Good afternoon, everyone. Thank you so much for that very kind introduction. As you said, I'm Ann Thompson. I'm the Executive Vice President of Architecture and Design at Related Midwest. And I can't be more thrilled to be here today with you to talk about trends in the design of tall buildings, but from the perspective of a developer. I can assure you that my presentation today will be the least technical that you hear this afternoon, but I hope equally informative. As it was said earlier, I am a developer, but first and foremost, I'm an architect. And I think this dual role gives me a kind of unique perspective in our industry. I know that those of us who design and build find a sense of awe in the tall buildings that we see, regardless of the height. In my 30 years building tall buildings, this has never waned. But I have to say that the interest in tall buildings really transcends expertise. Tall buildings give everybody a sense of awe because they defy what seems possible. They also measure our technological progress. The form has, in a very literal way, grown up over the last 140 years. We all know that the first skyscraper was just 10 floors high here in Chicago, and now we have the Burj Khalifa that soars over Dubai at over 2,700 feet. By any standard, that is kind of incredible progress. But the truth is, it doesn't take that kind of height to inspire wonder when you stand in the shadow of a tall building. These buildings defy gravity, kind of literally, while having a gravitational pull all their own. We've all experienced driving into a city and spotting a tall building from many, many miles away, and it compels you. These buildings are iconic. We all know the Burj Khalifa means Dubai and the Petronas Towers mean Kuala Lumpur, or I assume everyone on this call does. But when one of those buildings goes up, what we know is it changes the skyline of a city. And in many cases, it becomes a symbol of that city's spirit of innovation and prosperity. I also think tall buildings move us because they mark an era and they say something about the values of who we were at the time we built them. So if you take, for example, the Empire State Building, it reflects the optimism of post-World War I construction and contrasts painfully with the Great Depression that followed. The Willis Tower was the Sears Tower at a time when my parents and grandparents were flipping through the Sears catalog. And you can see in its design the self-assurance of a 1960s Chicago, the power of the city's industry and its ability to muscle its way to the top. I'm sure many of us remember the first glimpse of some of these tall buildings and how you felt looking up from the bottom or looking down for the top. It is unforgettable. But even though these buildings inspire so much wonder, they're not magic. We all know they're science. These buildings push the boundaries of the most advanced technology of our time. But it's not just about height. It's about what you achieve within that height by responding to the biggest challenges of our time. For instance, it's about density you can build to address population growth in urban centers. It's about energy efficiencies you can create to respond to climate change. That, to me, is the biggest trend in tall building design, that we are no longer solely interested in how much it costs or how quickly we can build it, how tall we can build, or how we can look in pure form making. We are still interested in how much it costs. Let's be clear, I am a developer. We do care about how much it costs, but we are now equally focused on how to employ new technologies for purposes well beyond reducing costs or shortening schedules. We have to be just as concerned with the impact of tall buildings on the communities they serve. And those impacts must be figured into the process from the very start, from day one. I would argue, in fact, that to do anything less is unconscionable, because these are buildings with a strong visual, societal, economic, and environmental impact. We cannot fail to look as far into the future as possible and attempt to understand what it will mean in 10, 30, 50, or even 100 years. Many of the buildings we design, as you know, will exist well beyond our lifetimes. So it is imperative that we are intentional about the legacy that they leave. At Related Midwest, this is kind of a fundamental shift in thinking for us. I started here about 25 years ago, and frankly, we were a group of young upstarts really learning how to build buildings. But as our experience collectively has grown and our expertise has grown, we have been able to consider the deeper contributions this kind of work can have. And now, at the start of every project, we ask ourselves, how can we leverage our work to bring the greatest positive impact to the communities we serve while addressing the generational challenges of our time? As an example, think about the impact that innovation in tall building can have on a city like Mumbai, a city of more than 20 million people. Mumbai has grew by 8 million people over the last 30 years, and it's forecast to grow another 7 million in the next 12. If done right, tall buildings can be a key to managing that population growth without jeopardizing people's health or sense of well-being. Or again, think about the impact in a city like New York, where the cost of living is climbing out of control because of the lack of available space to build new supply. Again, if done right, tall buildings can help to create affordability where there is almost none, and that's in a city that is powered by service workers and hardworking immigrants. Innovations in tall buildings that help us to build faster, smarter, and more economically can be a force in addressing housing shortages across the world. So now I want to talk a little bit about what does it mean to do it right. Let's take a few minutes to talk about that. When we think about big trends that support innovation in the design of tall buildings, one of the things that first comes to mind is emerging technologies and assemblies that help us build more efficiently and conserve natural resources. For example, consider glass high-rises. They are striking by anybody's estimation. Chicago has many, many buildings in downtown with glass facades. And I happen to live in one of them. And when the sun sets, those glass panels become unbelievably brilliant and as if they're glowing from within. But as we all know, glass high-rises have typically been some of the worst offenders when it comes to energy efficiency. Those incredible views come at a real price because glass, as you know, leaks heat in the winter and it turns rooms into saunas in the summer. Those glass facades have also had a devastating impact to the migratory bird population in Chicago. But now we have advances in glass technology that can address these concerns. They can reduce energy consumption and CO2 emissions. We can also now build smart buildings with demand-controlled ventilation, adaptive HVAC and lighting systems, and on-site solar power. And these are the kind of technologies that we are interested in pursuing. Another big trend we are following at Related is mass timber. We've been interested in this for quite some time. I think we're now only starting to see some of these structures being built, but it's clear that mass timber will become more widely adopted as people and cities recognize the sustainability benefits of the material. Its positive impact on human psychology and the sheer beauty of buildings constructed out of wood. I hope I have this fact right. But the tallest mass timber building is currently the Ascent MKE building in Milwaukee, as far as I know, at 284 feet tall. But I know that there are many, many more structures in planning and construction around the world. And for us, that is a very exciting trend because of the impact that this technology can have on climate change if it is adopted globally. As many of you know, the built environment is responsible for 40% of greenhouse gas emissions worldwide. Mass timber construction has the potential to dramatically reduce that percentage, to reduce the greenhouse gas emissions of our construction industry. In addition, mass timber requires less energy, it produces fewer emissions, it's a renewable resource, it sequesters carbon over its entire lifespan. And unlike other structural systems, it can be taken apart and reused more easily. It's easier to build with, and it's even quieter to build with, which if you've ever lived on the block where a new building is going up, it's pretty appealing for city dwellers. It also makes the natural environment a real part of our built environment, which has a remarkable effect on people's mental and even their physical well-being. Studies have borne out this idea that being surrounded by natural materials can reduce stress, which is something I think most of us can attest to from personal experience. Mass timber creates a sense of warmth and connectedness, which you can argue is something increasingly missing. It's an exciting innovation with layers and layers of a potential impact on our communities. And those are the kind of emerging technologies we are interested in pursuing. We're a company with a long-standing commitment to sustainability, and our hope is that we move towards not just net zero buildings, but energy positive buildings that deliver even more benefits to the communities around them. Now I'd like to talk about another trend that we are following closely, and that is one of adaptive reuse, particularly of mid-century high-rises. Cities around the world are full of buildings that have largely outlived their original use, and in many cases aren't architecturally notable enough to justify preservation on historic grounds alone. But when you're faced with demolition or reuse, we're seeing a lot of cities embrace adaptive reuse because it can be dramatically less costly than rebuilding from the ground up and far more environmentally sensitive. We have a history of adaptive reuse at Related, and it continues to be an area of focus. In fact, my very first project here was the adaptive reuse of the historic Mayfair Hotel on Lakeshore Drive. We converted that building to residential. Then, about 10 years ago, we also worked on 111 West Wacker, which many of you may know. It's another legacy project for us that was adaptive reuse of a different kind. The site, we acquired the site with 25 floors and 40,000 cubic yards of concrete in place. But the project had gone defunct and bankrupt, and we acquired the site with this 25 floors of concrete standing vacant. And it really stood as a symbol of the 2008 depression. And it stood that way for over 4 years. The structure had been designed to accommodate a 95-story hotel project. But through the creativity and the collaborative efforts of our entire team, we reimagined this project as the largest residential project on historic Wacker Drive and the Chicago Loop. And now we are taking all of that expertise and we are completing design and hopefully going into construction this year on a project we call 400 Lakeshore Drive. 400 Lakeshore Drive stands on the site of the former Spire, designed and conceived by Santiago Calatrava. When we acquired this land, we also inherited $50 million of foundation work that was in the ground. So we again assembled an exceptional team at SOM to help us understand the best path to utilize this existing foundation. It will be an incredible contribution to this project, and again, has helped us not only conserve resources, but reduce cost and schedule to build this project. So as you can see, well, we can extend the life cycle of existing structures, or I guess in the case of 400 Lakeshore Drive or Wacker partial structures, we reduce waste because we don't have to manufacture as many new materials or deal with what remains after we demolish a building. As the saying goes, the greenest building of all is the one that's already built. One of the case studies I've been actually following personally is the Tour Montparnasse in Paris. It's a fascinating building that jets up above a whole sea of low-rise buildings, a little bit like a sore thumb. Frankly, it's not that attractive of a building, and it's been unpopular with Parisians ever since it was built. But now it's undergoing a massive renovation envisioned by a design collective named Nouvelle AOM that will bring it into the 21st century. And they've imagined a new innovative program, a vegetative facade, and exceptional energy efficiency. It is designed to be a prototype for how mid-century high-rises can be reimagined. Tearing the building down to replace it with new construction certainly was an option, but it would have been more costly and required more resources. And it would have caused Parisians to lose this part of their city's history. Instead, this brilliant adaptive reuse weaves together the history of the structure with the technology and the innovation of today, making it an icon for our age. Aside from being a much smarter use of resources, it's meaningful for the people who live there. That historic quality, that kind of authenticity, which enriches a place at a society, isn't something you can really manufacture. You have to borrow it from the past. And yet, all of the benefits of tall buildings still apply here. You can make them sustainable, and you can turn them into whatever a community really needs in that time. It's a kind of project that's exceptional because, again, the layers of impact it brings to a city at large. And those are the kind of projects that we are looking at here at Related Midwest. And that's why I'm excited to see this not only this project, but the many other adaptive reuse projects around the globe come to fruition. Chicago is arguably the home of the mid-century high-rise. It's something that architects and engineers around the world look to in Chicago. These towers were the innovators of their time. And as Chicagoans, we are excited to see how we might reimagine those buildings for our community and provide the kind of design leadership Chicago has long been known for worldwide. There's one final trend that I'd like to leave you with today, and it's less about kind of what we build or how we build it, as it is about who builds it and for whom we build. Let's take the second part first, the who we build for. I think it's fair to say that tall buildings have a kind of mixed history. In some contexts, they have symbolized wealth, privilege, and power because they put people high up in the sky where they literally are above the fray of what happens to everybody else around them. They become untouchable. In other contexts, tall buildings have been used as public housing structures and made into symbols, if not actual tools, of poverty and oppression that, when combined with the public policy, have led to devastating generational trauma. Today, we're seeing a different approach to tall buildings that value their ability to foster community by making high quality construction more economically accessible to a much broader segment of our population. In Illinois, for instance, there's a law that incentivizes developers to set aside 20% of new units for affordable housing in new multifamily projects, which is creating not just mixed income communities, but tremendous opportunities for lower income individuals and families to live in high quality housing and in neighborhoods that would otherwise be completely out of reach. That puts people with closer proximity to jobs and public transportation and good schools for their kids. This shows us how architecture, development, and policy can work hand in hand to create healthier communities that don't exasperate the social problems of our time, but really work to chip away at them. We really need more of that, and it's something at Related Midwest we are working very hard to achieve. Our newest high-rise is in Chicago's Fulton Market neighborhood. It's called The Row. And it's the first that we have done, completed under this Illinois 80-20 legislation. And I believe it will be a model for what a more equitable approach to housing can look like in tall buildings. And now let's go back to the first part, the who builds. I've talked at length about the impact that tall buildings have on our society. And I think it's important to acknowledge that our industry generally lacks diversity. And what I find unfortunate about that is that diversity means fresh ideas and perspectives, and it leads to real opportunities in the communities around us, the communities we all build in. If we are truly interested in the ability of our work to create lasting change, we can't just think about skylines and awards or costs and schedules. We have to think about the potential for this work to transform lives, create careers, and inspire entrepreneurs. We have to introduce young people to careers in this field, especially those who normally would not have that opportunity to learn about our path. These things aren't distinct from our work as innovators. Truthfully, it's central to it. These are new directions from which to approach the problems we solve through architecture and through design. For example, instead of only working to create more affordable housing, we can also provide skills and training and mentorship that help reduce the wealth gap in the first place. We can mentor and employ a more diverse set of individuals to broaden our collective perspectives and understanding. It's something at Related Midwest that we have invested in heavily, both ourselves and through our partners, and these efforts have helped to launch dozens of successful small businesses that are providing essential services in our industry and building generational wealth that builds their families and communities. We've also looked to change the profile of our design teams, giving opportunities to firms led by people of color, in the hope that our projects will more closely reflect the communities in which they exist. When we acknowledge that each of us has blind spots created by our own particular life experience, we can understand how badly we need to help each other see the things we otherwise wouldn't. So I really hope that after today, you'll think even more about how diversity can make us all stronger and more innovative, how it can make us better designers, and what that means in each of your own firms. Because if we're going to overcome the challenges of our generation, we have to commit to strive for this diversity, equity, and inclusion, both in our personal and professional lives, and work to create a more equitable and prosperous future that benefits everyone. And I want to say that these words are for all of you, not just the names on the signs of the firms we work for. Every day, each one of you is doing the work, transforming the cities we live in and building a future that our grandkids will inherit. Excuse me, that our grandkids will inherit. We are the quiet change makers, but be clear, we are change makers. That's why these symposiums are so critical. They give us a forum in which to share ideas and help our profession evolve even faster. I really do believe we are living in an exciting time where the advances in innovation in tall buildings will transform the built environment. They will transform the places we live, work, and play in ways we cannot yet even imagine. So I hope you will all leave this event inspired by all of the speakers here to do great things and leave behind a great legacy of building. But that sense of awe you inspire in everyone isn't just about the height, it's also about what good you are able to achieve within that height. Thank you very much for the invitation to speak here today, and I am happy to answer any questions.
Thank you very much, Anne. Thank you for an outstanding presentation. Bar high and setting the tone for our event today. And thank you for sharing your vision for responsible and environmentally responsible design and development. We are going to allow audience online to unmute themselves and ask questions, as well as students and other audience members in the room. We're going to take questions. And while we do that, let me just go back to my PowerPoint presentation, and while did it work? I was going to show some of the, there we go.
Oh, thank you.
Some of Anne's buildings that she talked about, 111 West Wacker. That's the building that she mentioned was what, 25 stories tall? When you,
it was 25 stories of concrete.
Yeah, it was, and Shankar was the structural designer for this. He used to say that this was the tallest the strongest 25-story in the world, because
it is true.
and the project stopped, and then Related Midwest acquired the site, and a couple of other projects that Anne mentioned. This project, and
this is what we call the Row in Fulton Market.
Yeah,
this is the building that I spoke about that is utilizing the 80-20 affordable housing legislation.
And what is the status of that right now?
We will be finished in June 1st.
Excellent, very good. All right, thank you. Questions? Anyone in the audience here? Any questions? Anyone online? Feel free to unmute yourself and ask your question. Are there questions in the chat? Any questions? Once, going twice. All right. Thank you very much, Anne, again, for your outstanding presentation. We're very, very grateful to you for your continued support of our students by sharing your time and expertise with our students. We're very, very grateful, and we're proud that you are one of our alums, and we hope to have more people like you and other speakers that we have today. So let's give Anne another round of applause, please.
Thank you so much.
Thank you, Anne. All right. I'm not in the oops, what did I do? Let me move on to the
is it too late to ask any question as a developer?
No. Anne, are you still there?
I'm still here.
Okay.
Yeah, since no one is asking question, I have a questions for an experienced developer. How do you see the trend of modular housing and modular construction, the market, and the acceptance by developers? Because there have been so much technology and experience gained in all these years, but it looks like the modular housing it still has not taken off in a big way to solve our housing problem, our homelessness problem. This is so everyone knows that it is quick, simple, and fast. But I don't see any developers or anyone is jumping into this bandwagon.
No, we haven't. It is interesting. We have explored this a little bit, especially with our affordable housing portfolio. And we are very interested in modular housing. At the quality level that we build, we have not found it yet to be economically feasible in most of our projects. When you're building affordable housing, there are very strict requirements in terms of the quality of construction, dimensions that we have to meet. With those requirements and kind of codes and things that we need to follow, we have not yet found a modular product that we can build in a way that is actually cheaper than a stick-built kind of product. So I think that is in part. Now, I do believe that that will change over time. I know that there is continuing advances. The other kind of barrier, at least in Chicago with affordable, is when you are building at scale and trying to use modular, there is some reticence from the unions because we are a union town, and so it is difficult for them to embrace that as a technology yet. Again, I think that is changing, so I think its time will come, but at the moment we are not yet embracing it, at least at scale.
Yeah, I share with you these restrictions we are facing in our country here, because recently I'm working with clients in Eastern Europe because they want to rebuild Ukraine, but after the war, but the rules have been relaxed or accommodating and adaptive in order to solve the immediate crisis.
Exactly.
So, and also, of course, the manufacturing costs in the United States always another challenge for cost. But anyway, there are many resources worldwide we can solve this problem. So I just hope that in our industry, in our community, people can work together and face reality rather than the idealism to solve every problem. We have many people sleeping on the streets that I saw in any major cities. That breaks my heart. So I just want to share this with everybody here, that we are ready, we can do it, modular housing successfully, if we can and work together. Thank you.
Thank you, Dennis, and thank you, Anne. And we have a couple of other questions from our audience online. Arun, you had your hand up.
Yes, hello.
Go ahead.
Yeah, to Anne, to the developer, how does sustainability impact at all when you're designing or when you're considering a tall building? Is there anything that you?
Yes, yes. We have a long history of being committed to sustainability, and that's especially true with our tall buildings. We actually, we built it we finished it in 2008, a building called 340 Randolph, and it was the first LEED certified high-rise, I think, in the Midwest, if not in the country. And we've continued that commitment, and it is a conversation that we have. It's one of the things it's very different is we now have that conversation day one when we start a project. What is the sustainability narrative? What is the sustainability goal for a project? It has a lot to do with energy efficiency, as much as anything. Of course, we're also looking at using renewable materials. We're looking at low VOC. We're looking at transit-oriented developments and all of those things that contributed to sustainability. But a big part of it is energy efficiency. So we're looking at that relative to our facade systems, our mechanical systems, and trying to achieve the kind of balance that we need to be environmentally appropriate.
Okay, that sounds great. Yeah, thank you.
Thank you. John, you have another question?
Yeah.
John,
Hi. So I'm a graduate student at MIT conducting a thesis on like tall buildings, or tall timber buildings, and starting to realize that a lot of these tall timber buildings are becoming really, they're actually, structurally feasible and efficient. So I was curious, and on like the developer side of things, what could be hindering the tall timber movement? I was just curious.
To be honest, a little bit is familiarity. So some of it is, I do think you will see taller buildings take shape in Chicago and in other cities. Of course, in Chicago, we have the Chicago fire, which, sort of sticks in everybody's mind. So kind of getting past some of those conversations is one, particularly when you're talking about high rise. Second, though, whenever you're introducing a new technology like that, it's also about building expertise in the trades to build that system. So I think as it gets introduced in smaller structures and construction firms gain more expertise in that assembly, I think that it will help advance the height of those buildings.
Yeah, no, that's definitely a good point. I feel like
Because that obviously
yeah.
also affects cost, right? So if they're unfamiliar and there's a lot of unknowns, they're going to price that building appropriately.
Yeah, see what you're saying. Thank you.
Thank you. Any other questions? Yes, we have a question.
About modular architecture, moving forward with that, now we see parametric architecture also being utilized in residential to a mid-rise extent in the European countries. Do you think that trend could come in tall buildings as well? And what would be the major consideration as where you are allowing the users to choose the unit which they like based on their priorities, but then again make profit out of it?
Okay, let me see if I can summarize your question. I'll try.
I couldn't
No,
quite
but-
hear, so.
The question is, you talked about modular design, but there's also parametric design. And how do you foresee designing for individual tenants, right? Or desires in terms of daylighting? Is that? Or
Based on the parameters, so people are allowing combinations to come where you need one kitchen or like one bedroom or a living space.
Oh, so people can basically customize the design of their unit.
How can they customize the full design of their unit?
Right, is that right?
Well-
Is that the question? Yes.
Yeah, whether it be how you daylight or the interior
Right.
design of it. It's interesting because at the start of my career with Related, part of how I came to be here is we were allowing people to fully customize. At the time, it was condo product, not rental product. And that is a very difficult process when you allow that. We have sort of switched our path in that regard and have now moved to a system in which we put a lot of time and effort into the design. Back in the day when we were allowing for customization to sort of offset that cost, your initial finishes might be a little less than someone might like, but knowing that they're going to change a lot of them. Now what we do instead is we work with an interior designer and architects to design those finishes to a very high level. And when we keep it the same or with moderate choices, we can give them a much higher level of finish, which we find people to be very happy with, because what they're buying isn't just a set of finishes that you tick off in the box. Yes, I have a granite countertop and I have wood cabinets. What you're buying is design, which a lot of people cannot afford to have the work of an architect or designer design their home. But if you're living in one of our multifamily buildings, you're getting that just by being there. And so people see that as a distinct advantage. Now, so each building has a particular perspective on what it looks like. That being said, we do often give people some ability, to make their unit become more personalized, whether it's in window treatments or wall covering, or they can switch out light fixtures, things like that. But we tend to keep it to those things that are a little easier to switch in and out, but the basic finishes stay the same.
Excellent. Thank you very much, Anna. Again, thank you so much for an outstanding presentation. We're very, very grateful to you. And John, you asked about, and Anne mentioned the Ascent Tower in Milwaukee. And we have a presentation on that particular project that will very, very detailed. So hang in there. All right, let me move on to our next presenter, who is Dennis Poon, then managing principal at engineers. He has more than 4 decades of experience in analysis of a wide variety of building types, such as super tall and mega tall structures, mixed-use development, hotels, sports, arenas, and residential towers worldwide. He specializes in the application of the state-of-the-art engineering technologies for building analysis, design, and construction, including project delivery strategies. Dennis has extensive experience in size investigation and optimization of structural systems. He leads iconic projects throughout the world, and he also seeks to push the boundaries with cutting edge projects. That provide engineering and analysis, space factor, habitat prototype, which won NASA and Bradley University's 3D printed habitat challenge. This is project. One is Taipei 1, and I don't mean to steal your thunder, Dennis, but just for the benefit of students, and I apologize, Dennis, if you're going to talk about this aspect. Architecture students, you think that wind forces on a building, which are tall buildings, extremely critical. We cannot change the direction or the speed of wind, but we can design our structures, our buildings, such that the forces will be perhaps reduced. In this particular case, maybe it's part of Dennis's presentation. It's an excellent example of how you can design the architecture to reduce those forces. Design of Shanghai Tower and Penang, which I believe is in Shenzhen. Let me stop sharing screen, Dennis, and I will turn the virtual floor to you.
Yeah. Okay. This one? Try to get the power.
Why am I still seeing the old? Hold on. Still seeing the old. I stopped. Mac is here.
You see, everyone sees it?
Just a
I think
moment.
it's good, Abbas. We are seeing Dennis's screen on Zoom.
Oh,
This is this one.
but it's not on the.
Yeah, it's just.
This is you guys online are still seeing my screen, right?
No, Abbas, we are seeing Dennis's screen, I believe.
But we're in the room, we're not.
I have the design of tall composite structures.
See,
It's their classroom.
Yeah,
okay.
we're seeing Dennis's opening slide.
Okay,
All right.
okay, Abbas, can you see it?
Yes, we can see it. And if I could
Okay.
ask everyone to please mute your microphones except for Dennis. Dennis, thank you. Go ahead.
Hello, good afternoon, everybody. And I try to make it quick so everyone can go home and enjoy the Friday afternoon in the nice spring weather. Because I want to go home too myself. Well, anyway, thank you everyone for this opportunity to listen to the sharing of my experience through 45 years working with TT. It has been a great experience, and I'm fortunate enough to gain a lot of work and good projects opportunity in a nice company. And we are actually learning every day and evolving every day. And as you see, how we start our design and construction and building industry, we always evolving. From a small house into the Calatrava, no, not the iconic building in Barcelona, and also from Petronas Tower all the way to the Kingdom Tower. We always evolve with technology and learning process. This is from the CTBUH latest slide showing the constructed world tallest building, and our company and my team has been fortunate to involve with quite a bit of high-rise building. And basically, I want to draw the attention that the definitions and the guidelines for tall buildings. So when we reach about 300-meter tall, we call this structure identified as super tall. But once we go above it to 600 meter, it is mega tall, like the Shanghai Tower, Ping An Tower, and Burj Khalifa, and so on. But we are not competing for height nowadays. As Anne has spoken before, high-rise building really have a lot of contribution and factors and different reasons why they were being designed and built. It always, for engineers and designers like us, it will always push us to the forefront of technology and keep thinking and keep us on our toes to continue to face upcoming challenges. However, we always have to deal with the natural factors of wind and earthquake forces. So back to the basic again, how do we cheat the winds and work with the architects and create an iconic urban structures? So basically, you can see most of the high-rise building, we try to taper the building as it goes up. It is great to reduce the wind load, because as we move up, the wind pressure is always higher at the top. We don't want to put a big sail, like a sailboat on the top, to catch more wind load. So tapering the top always give us the reduction of wind loads. And also it lowers the center of gravity of the building to much lower to the ground and give us more stability. And also it makes the building look more less obstructive at the top and give more view at the sky. So, and for the Shanghai Tower, it's also a tapering, but we do one step further. We are also twisting the shape, twisting the tower exterior skin. I have to emphasize, we're twisting only the exterior skin in order to reduce the wind load. We're also tapering it to reduce wind load, and also we're creating notches on the side of the building to cut down the vortex shedding effect. So there are all kinds of engineering solutions, working with wind tunnel tests, working with architects to create the best architectural forms and best engineering solution. Vortex shedding is one subject we all have to pay attention to when we design even any low-rise or high-rise structure. Vortex shedding is a phenomenon when wind, vortex is a spinning and the turbulent flow of fluid. When you study the fluid dynamics, it is an unsteady flow. When wind is blowing towards a building or an object, we will go around the building. When it goes around the building and wraps around the building, it will create a vortex, and it's like a turbulence flow. And this is a current wind load. And when you go on one side and you go to the other side of the building, it will create a negative and alternating in low pressure zone that cause the building to move in a crosswind direction, oscillating the building. It will create not only the drag wind effect, it will also create a crosswind effect. Now, for super tall building, when the building is very slender and the slenderness ratio taller than 10, slenderness ratio is defined as the width of the building divided by the height. Okay, so if the aspect ratio is high, that means your building is very slender, which is that's the wider you are and the shorter you are not slender. But the skinnier you are and the taller you are, it becomes slender. In our industry, we think that tall buildings from 9 actually it's not from 10, from 9 to and up is a slender tall building. And when you have a slender building, it's more possible for slender building to suffer and to have the vortex shedding effect. If you see from this slide, okay, vortex shedding, when wind blows towards it, it will create a vortex effect. And this vortex effect will create alternating negative and low pressure zone, causing the building another crosswind in this direction. Even the wind is blowing along the object, it will create a crosswind. Sometimes a crosswind pressure can be higher than your drag wind pressure. And the best shape to minimize water building shape of a building is a circular shape or a square shape or building with slot for wind to pass through. The worst shape will be a triangular building. Okay, this is a more diagram indicating the vortex shedding. I'm sure your professor in the faculty will continue this subject in a more detail. And this is the crosswind that is created as a byproduct of the direct wind, a long wind blowing towards the building. And sometimes this wind can be high. So when you have designed a building, when the wind is blowing this way, you also have wind to design for this other direction. You have to design the building for a combination of load in both X and Y axis. So you see this how the crosswind will cause the building to move in the other direction. How do we solve the problem? When I start working with Taipei 101, we work with CYE architects in Taiwan and the wind tunnel test out of EI. We did different wind tunnel tests. On Taipei 101, we decided to change all corners of the Taipei 101 into stagger corner with recessed corner. So we have corner, we did the corner setback. So on Ping An Tower, which is a 600-meter tall tower, which is in a lot of typhoon zone in Shenzhen, China, we also provide recessed corner in order to break up the vortex. So the reduction of wind load has a lot of benefits to your building and the construction cost and the comfort level. It will make, if you reduce the wind load, you make the tower core smaller, and therefore you can have less wind load and smaller column sizes, and by reducing the wind load stress. Then if the core is smaller and the building member sizes is smaller, your building weight or building mass is smaller. When your building's weight is smaller, you reduce the earthquake forces due to the weight or the mass of the building, because seismic forces is a function of the mass of the building. And then when you use less material, you reduce the carbon footprint. So it is a very important issue for all of us designing or engineering high-rise building. So Taipei 101, we create a series of recessed corner, and actually creating all these staggering corner will create more corner office for the executives and for the high-paid people. So, and more view. So people love it. Why not? It's a perfect solution. It's a win-win solution. On the Incheon Tower in Korea, which was designed but was not built after the change of mayor, we also provided an open slot between the buildings for the wind to pass through, and also individual slots, wind slot for the wind to pass through. Just try to minimize vortex shedding effect. On the Wuhan Tower, which is constructed without the tower crown due to the height reduction, we also created a lot of recessed corner and also wind slot. So show you some of the examples how we can optimize the building architectural design through engineering efforts. You see, when wind load goes up, the wind pass through. So we even have to talk about how we treat the tower cap, because the aerodynamics of the tower cap, okay, will affect the vortex shedding. You see all the corners and the curvature. It all has a function on the wind load effect. So wind slot were created and building taper, and we try to optimize the tower crown with wind to pass through. So we went through a wind tunnel test with our ally, with our colleague, RWDI in Canada, and we run different wind tunnel tests to find the optimum solution. So this is some of the effect and how this thing will, you can see the vortex shedding and the induced vortex shedding effect. Is you cannot cheat. So after that, we try to work with the architect how to create a wind slot and optimize the architectural form without any effect. So the end result is a more efficient structure, it's a cost-effective building, and works. Now, another phenomenon when we deal with high-rise building, is the issue of acceleration. Everyone knows that all the building will deflect, will move due to wind or due to high wind, okay, or it will move in different direction. It is not the movement and the amount of deflection that people will feel. People will feel the motion, the building motion, due to high acceleration of the movement. The large deflection of the building will have a bad effect to the building finishes, your door frame, your partition walls, your curtain wall finishes. Curtain wall will crack, curtain wall will pop if you have excessive deflection. And then if you deflect too much, you introduce a lot of stress and strain to your building members. That's no good. However, for the occupants of any tower, the acceleration is the perception that makes you comfortable or not comfortable. People will feel the building movement if you have excessive acceleration. And building acceleration is affected by the building natural frequency, the building frequency. And building frequency will be affected by the stiffness of the building and the mass of the building. Concrete building and composite building provide you a better a higher mass, because concrete is heavier, gives you better mass damping. And the stiffness of the building depending on your structural system and your core layout. Sorry, I get a call. Let me turn it. So when we have to deal with building acceleration on the building, we have to pay attention to how we manage the building mass, the building stiffness, and also the building stiffness also affect the building deflection. And this is something, but in addition to managing the building mass, managing the building deflection due to engine design, we also have supplemental method to manage and control the human comfort. So the criteria, general criteria of building acceleration limit due to 10-year wind. For residential, we try to limit it to 50 milli-G to 18 milli-G. For hotel, sometimes can be 18 to 20 milli-G. Office can be 20 to 25 milli-G. The thing is, it depends on the owners and the sensitivity of the occupants. We have owners who ask us to design the residential part of the building not to exceed 15 G and only limit us to 10. Especially hotel, sometimes the hotel owner will tell us we don't want to take a chance with our hotel guests who complain about building movement. We want you to limit the hotel building acceleration to a lower number, maybe to 15. Office, generally people accept 20 to 25 because they don't sleep or they don't spend all day in the office. Now, what are the supplemental damping system? One of the most common method is using a pendulum. It's a passive damping system. We hang a mass either in concrete or in steel, and we dampen it. The function of a TMD damper is like when you are a child is on a swing. When you swing, when you are swinging, when you swing up your legs, you know your swing will move up more. But when you want to slow down and get off on the swing, you kick your legs in the opposite direction. So this is the basic behavior of a two-mass damper. It's a pendulum. So when the building is moving in the other one direction, you tune your dampers to activate it to swing in the opposite direction to counteract the motion. Now, how much you have to hang it? Usually for high-rise building, you need 2 to 3 story cables to hang with a few hundred tons of steel plates to hang this pendulum in order to be effective. So, but sometimes when you're short of 2 to 3 story high space to install this, you can use a double hung TMD as shown on the picture. Okay, this is one of the pendulum we are using in Taipei 101. We created a steel ball painted in gold color, and it's about 3 story tall. And we open up the space as a sky restaurant and a sky observation tower. This is the one in it become a tourist attraction. And this damper did move during even earthquake and high wind, and it become an attraction. When people see it moving very slowly, they feel more comfortable because they know that the engineering works in this high-rise building, and it also function a little bit in earthquake. The other one is Shanghai Tower, and the gray color you see that at the bottom, hung by cable, are several hundred tons of steel plates, and the designer put a sculpture on top of that to make it like a tourist attraction at the top of the building. So TMD is a very good device, and sometimes on residential building, when you don't need that much of damping, we have a water tank, and on the water tank we put control hose on it, and then you can make it like a tuned liquid column damper. So when the building is sloshing, the water get activated, it will be sloshing around and through the different valves and openings in the water of the gates inside the water tank. We control the water flow to counteract the building motion. Now another one is using viscoelastic material. We're putting it in a link beam, between concrete shear wall. So then the thing is, you have a two concrete shear wall, and then usually it's in the elevator lobby, you have a link beam. So when the building moves this way, it activates, it activates this concrete link beam. So we're putting viscoelastic material to absorb this movement and the energy to create damping effect. So this is one of, it's called toppling damper, is developed by 3M. It's a viscoelastic damper. So that's one of the damper. And the other one is like a viscous damper, work like a shock absorber. And sometimes we can put it at the end of the outrigger. When the outrigger is connected to the column, where this thing moves and moves, we can absorb some of the energy. So in addition to managing the mass, the stiffness of the building, the frequency of the building, there's supplemental dampers, which is a much cheaper way to do it. And there's another way, another one developed by Thornton Tomasetti in-house and without WDI, is the hummingbird kinetic damper. Because the water sloshing damper and the water tank dampers is too heavy and is using a lot of space. So we are using a series of air pipes connected to a series of water tubes, and we're using air spring control through the valve to control accurately how the water is moving inside the tubes. And it is very effective way to mobilize the whole volume of water inside the tube instead of the water sloshing dampers. So we can put these tubes below the mechanical room, hung below the mechanical room, or put it on the side of the building, and it's very flexible. So there's another effective way of damper used to manage acceleration and save cost of the tower. Now, another tool we have for high-rise building is our TT core group, continuously creating software development and computational modeling, research and development. As we continue to push the envelope in engineering, innovation, and good design and optimizing design, we need to use the new technology with new software development, and our TT Core Studio continuously working on that. So we do not lose sight on the importance of application of technology on all our projects, with automation, interoperability, because we have so many software, so many information sent to us from different trades. So how do we communicate among each trade? So we need software to be the traffic controller to do all the translation. We automate as much as possible so that we can study more schemes, we can do more visualization, we can do more accuracy in design. But the thing is, we don't want to see a bunch of computer numbers. So visualization will guide us where the problems are, do troubleshooting and more accuracy. and also structural AI, architectural intelligence. We use it extensively. Today, we don't have time, and each one I can give or share with you a lot of specific experiences on this technology with our company. We can reserve it for later day. Now, working with the architect nowadays, architecture and the other trades are using software extensively, and how do we deal with them? And we have to make good use of them to save time and efficiency, and also make our design much better. So we have to start generative design and parametric modeling of the architecture as soon as possible. In the old days, we don't do that much. We at the beginning of concept design, we say, there's only concept design. We don't have to do that much. We just do a little bit, and then design development phase, we just do a little bit here. Then construction document phase, okay, construction document phase, we have to put most of the engineering effort, and so on. So we are not putting too much effort at the beginning. Now the tide has changed. The tide, okay. Usually we on the concept design, we don't do much in the old days. We only do beam, tabular, and CATIA, rapid modeling. At the later stage, we don't want that. We want to push the generative modeling and beam design from the beginning of the design project. So we try to do a lot of work at the beginning, so that we do all the optimization and troubleshooting and how to optimize the design from the early on. And then we will have a easier time for construction document with all the data to give the contractor. It really lower the cost of design and also the ability to control costs. So generative modeling and BIM, we start from early stage as our trend and through generative modeling. So when we do parametric modeling, we have to work with the architects to go hand in hand. And then we have advanced software. Okay, everyone have been using Rhino, Grasshopper, and so on. And also we have our TT in-house core studio specific software developed that will enhance it. And you can see full parametric modeling. This is a design competition years ago in Asia, and the architecture have this kind of rendering. So if you have all this exterior curtain wall, how do we cope with that? So we went through parametric modeling and see how we can provide our primary structure and adapting the primary architecture exterior into our structure. So through a series of parametric modeling, we optimize our structure, system, and form at the very beginning, and then give it back to the architects and work with them in order to have the optimum design from the early on. And whether it's a composite structure or steel structure, it's the same. We have to work out the structural system primarily written. So you can see the ribbon, the chaotic or the random design of this design will lead us into a very, at the end, we created a very rational exterior diagonal bracing system that will fit into the architecture and hide the building, hide this structure within the curtain wall of the architect. So this is one of the examples. I have more slides on the other job, but I know I don't have time. Another issues for our design, another subject for our high-rise building design will be performance-based design. As we know, we are dealing with earthquake everywhere now in most countries, especially in Asia and developed country. They have a lot of seismic design. So our old style of linear earthquake design, linear analysis is no longer accurate. So we started performance-based design very on, more than 20 years ago. We are already working on performance-based design in a different level based on the capacity and the computer software we have. So performance-based design is a must an important subject for high-rise building design. And that's why we have to take our advanced dynamic analysis classes. It is very important. We have to know the dynamic design and nonlinear analysis. We are using time history analysis. We have to understand what's the seismic level we design, and then we have to know the material we are using, and then we have to consider the deformation base. And also, it is always a nonlinear analysis. Now, we also have to discuss with the owner what performance level we have to live with for your tower. If it is a hospital, or it is a presidential building, or it's an important military basis, or what kind of function, or it's a regular office building or residential. So there are different performance level. We started with operation level, which is after earthquakes, very light damage, and then building subject to very low earthquake and not economically to design for operation level under severe earthquake, because different buildings have different requirements and different importance factor. So we consider immediate occupancy requirement, we consider life safety, we consider collapse prevention level. So summarize it as a chart. We have some basic objective, and some of them, the very rigid one, will be we design for very rare 2,500 year return period earthquake, and the building has to be life safety if you have a very important building. So we talk to the owner what performance target we will be using for the building, and this is a discussion with the owner based on performance target. Now, after the owner and designer not agree on the selected performance objective, we develop our development design criteria and continue on this performance-based design. Well, we have to do performance-based. We create a mathematical model for tower structure. We do inelastic material property analysis with steel, concrete, and concrete intention, and study that. So we have to select the proper seismic curves. So on this job, we study the different curves in San Francisco, different curves in different parts of the world, look at the time history curve and try to calibrate it which to the way that is useful, and we scale it up and down to the level that can be used on our specific project site, because we have to do site-specific seismic evaluation, not just by the building code on high-rise building design. We do site-specific seismic evaluation and analysis and choose the right acceleration, seismic acceleration curve, time history curve to use. Now, so we also, then after that, we check the performance of all the beams and the shear walls. And then you can see the hotspot we have in our shear wall, in our link beam area with nonlinear dynamic seismic analysis. You can identify through visualization. We can go to this area and see how we improve it, how to design it properly. So it is a lot more accurate to provide performance-based design as for high-rise building. The old days of linear analysis is long gone. Now, another thing in our industry is 3D printing. I'm quite interesting because I always look into forthcoming trend in our industry. We cannot get away from 3D printing. 3D is here already, but for building, we can do a lot of 3D printing already with small bridges, maybe a lot of building units. I participated with AI factory on the Marshall 3D printing project. We use we basically provided a special material to do a printing and participated with the NASA. So you all will have your opportunity to participate in upcoming opportunities for 3D printing in our industry, from small houses to mid-rise building, to maybe to high-rise power in different way. So machine learning is also part of our daily lives right now. We always have to accommodate it to AI and machine learning. And our TT has been so committed to it. And we have a lot of database in our AI that will help us to advance our design and optimize our design. We have software we developed and how we work with all our clients to optimize it. So sometimes size and talent matters, and I'm lucky with our founder Thomas Hetty group, and everyone has been able to on the forefront of technology. That I encourage all of us to stay on the forefront. That's how I have the opportunity working with my team on so many challenging projects, because we have the tools and the experience to do it. Now, I just give you I have 4 or 5 towers I can talk, but just I picked one of them because time is running out. Wuhan Tower, Greenland. It is in Wuhan. Everyone knows Wuhan after the COVID, but that is still a very controversial subject where it happens. We're not going to go into it. I was in Wuhan many times, and so far so good. I come back okay. Wuhan, this landmark building is designed by Adrian Smith with a structural engineer. We are working with local engineering firm Icardi here. It's supposed to be 606 meter tall, but after we design the building and start construction all the way up to this almost 75%, the government said you cannot build 606 meters. You have to cut it down to about 500 meters. So we lower the ground after that, but this building is finished. It's still close to 100 story. But this is the building that we have utilized all the things. I have all the tools I have discussed about how to cheat the winds, how to make the building taper, how to do the wind slot and acceleration control, and all the high tech we're talking about. So since it's a hotel on the top floor and hotel there, apartment, so we have to make sure our building acceleration is below 15 or even up to 10. Office, we can have the acceleration much lower. Okay, so
Yeah, we're almost out of time, Dennis.
Okay.
Actually, we are.
So anyway, I think I can just go through this very quickly, and you can see the aerodynamics, and then again, I want to show one more slide that is important for the framing. So you see, this is the core. We try to, this is a composite concrete core with steel buried inside, and also we provide the perimeter column. We try to use the full width of the building by using outrigger truss, connecting the core with the outside column. So we're using the full width of the building to increase the stability of the building to make the high-rise building stable. So this is the composite concrete core, the perimeter super column for the tower. And this is the extensive use of the outrigger trusses on the mechanical floor, the beam system. So, so anyway, next time we can talk to you more about different buildings, Shanghai Tower, and so on. I want to conclude this way. And you see, we use, even with the shear wall, we use a lot of, sometimes we use steel plates inside the shear wall so that we can reduce the congestion of the rebars and also take higher strength steel. This is some of the Shanghai Tower. So since we don't have time, we will leave it for the next opportunity when we meet again. There are many interesting projects we can discuss. Hopefully, I can make you guys interested more into new technology and keep exploring for another new frontier. We have many good colleagues, many people in our industry drive this. But as I said in the beginning, I really want to see how we can use our experience to push forward to build more housing for the public in order to not only just all the good, beautiful building, but buildings that are used for the general mass in the next round of discussion, because housing situation is a worldwide problem with the population. So hopefully we will pay more attention to it. Thank you all.
Great, thank you very much, Dennis. I appreciate it. Outstanding presentation, really great. Thank you. We're very grateful to you for sharing your time and expertise with our students. And I hope that, let me step over so that maybe you can, Mackenzie can start Professor Polakowski's presentation, get it ready. I hope you understood from his presentation that architecture and structural design of tall buildings go together very, very closely. He talked about the Taipei 101, how the corners were designed such that to Dennis, I used to remember the percentage, the wind forces that were reduced. Was that 15% or higher, the reduction in force?
We can if we do it right, we can safely 15 to 25% of wind load. Easy.
Which is really significant because you design tall buildings primarily based on the stiffness that Dennis mentioned to limit movement and acceleration. So the lateral load resisting system that does that takes a lot of material. And if you can reduce that by even 5%, that's significant savings. So, and then he talked about other things that were, the other thing is to keep in mind that lateral load resisting systems of tall buildings are very dominant architecturally. They affect your architecture significantly depending on what type of system you use. So it's all very, very important for anyone involved in design and construction tall buildings to get together from day one. Some of you are in the integration class, so all the major players need to sit at the table from day one. The architect, the structural engineer, the mechanical engineer, the constructor. Everybody needs to sit together. So thank you very much again, Dennis, for a wonderful presentation. I'm sorry that we couldn't have more time, but I think we should have you come to speak to our classes or some other way that we can benefit more from your presentation. So thank you very much for your time and expertise. Thank you.
And I'm sure myself and my other colleagues will have a lot to share with everybody. I think we can make things much better moving forward if we work together.
Thank you. Thank you. That's great. So let me, are we ready? So let me introduce our next speaker, although he does not need much introduction, but nevertheless, we will do that. Let me just share my PowerPoint. It's downloading. Okay. I won't go full screen, that way you can jump in. Our next presenter is Professor Jim Polakowski. As you know, he's a principal with Datum Engineers in Chicago. He's also a faculty member and a Curvis Fellow. I'm honored to have him as a colleague in architecture. He's also a faculty member in the civil engineering department. He's a licensed structural engineer. He's a graduate of our program with a Master of Architecture with specialization in structures. He's been in practice for 27 years and he has led roles in several significant projects around the world, including world's tallest building, Burj Khalifa in Dubai, and OKO Tower in Moscow, Europe's tallest building when it was opened in 2015. Jim also is the senior project for was the senior structural engineer project for UIUC's building, campus instructional facility, campus structural institute, and he's a member of the Chicago Committee on High-Rise Buildings, American Concrete Institute, American Society of Civil Engineers, and serves on the Structural Engineering Association of Illinois Executive Committee. And these are some of his projects. And with that, let me stop sharing and we'll turn this floor over to Jim.
All right, thank you, Abbas, for that very nice introduction. I'm very proud to be part of the university here, and And I'm also very happy to be participating today and share some of my experience in building tall with concrete. You know, we're excited to put this year's symposium together to talk about advances in a number of different materials. I've been fortunate in my career to have a lot of experience building tall with concrete. So I just want to share some of that experience here today. So today's tall buildings really couldn't be realized as successfully without the use of concrete. So we're going to explore why through exploring tall building behavior, advantages of using concrete, tall building systems that use concrete, the properties of the concrete that we use for tall buildings, how we construct our buildings in concrete, and then some of the challenges we see. So first, just kind of some overview on tall buildings. So tall buildings are becoming more and more common, and so are taller tall buildings. And Dennis alluded to all the slender tall buildings. CTBH classifies super tall buildings as those greater than 300 meters and mega tall being greater than 600. And here's Dennis's mega tall building. So one of the, oops. I don't think this is the slideshow. This is an active. No. Anyway, sorry for the technical difficulties here. Anyway, so currently we have 4 megatall buildings and 211 super talls. Under construction, there's a lot more. Proposed, there's even more. And it's fascinating to look back, you know, just a little over 20 years ago when we had no megatalls and only 26 super talls. Looking a little closer at the top 10 tallest buildings currently, we see that we have 2 buildings. 2 of the top 3 are all concrete. Now they do use structural steel to create the spire, but they're essentially concrete systems. We've got 7 that are composite systems where concrete core walls used with composite columns. And then we've got Type A 101, which has composite as well. Looking at the rest of the 100, we see 31 all concrete. We see 53 composite systems and only 7 that are all steel. And of those 7 all steel buildings, 4 of them were constructed 50 years ago or longer. Only 1 has been constructed since 2000. And if we look at a chart that shows the materiality of tall buildings going back to the 30s, we see that steel really was the dominant choice for tall buildings up until the 70s. And then concrete started to come into play, whether it was an all concrete system or composite system. And this chart tops out at 2010, but if it would go beyond, you'd see this trend continuing. So why do so many super tall buildings use concrete? There have been continued advances in concrete material, as well as how to construct concrete in an efficient manner. And additionally, concrete has many inherent advantages that complement tall building behavior and design. Concrete provides greater stiffness to reduce drifts, provides greater mass to slow down motions, provides enhanced strength opportunities, and it also provides the thinnest floor plate to optimize building height. And Dennis started talking about slenderness ratios. You can, again, this is the ratio of a building's height divided by its footprint. And you can see as we've progressed with tall building design and heights, we're getting more and more slender. So it used to be a slender tall building was in the 6.5 to 7, maybe 8 range. And now we're seeing buildings up at 15, 23, 24. So we're getting more slender. And slender buildings do have different responses and requirements to the wind. In tall buildings, all tall buildings need to be designed to accommodate wind, resisting wind forces through shear, resisting overturning moments caused by wind forces, controlling the drifts, the motions due to wind, and also the accelerations. First, I want to talk about how wind hits buildings as a shear load. And when we have a large concrete core, it's very efficient in resisting that shear. Okay, but we also can utilize the building's perimeter to reduce shear, although most of it's still going to be taken by the concrete core. Wind also creates an overturning moment onto buildings. So we'll have a wind load that hits a building. It gets resisted ultimately at the base, but it creates this overturning moment. And that overturning moment gets resolved into a force couple that can potentially create uplift or tension on a structure. So that overturning moment, no matter how big your structural footprint is, that overturning moment is the same magnitude. So increasing your structural footprint decreases your moment arm. It decreases that couple. So just diagrammatically taking a look at if we only have a core, for instance, and then we have a building where we've expanded and engaged the perimeter, our moment arm, our structural footprint is much bigger. So we can then we can reduce the force couple. So engaging the perimeter not only allows us to reduce the uplift, it also allows us to increase our building stiffness because we're reaching out and grabbing all of that material that's as far away from the center of the building as possible. And doing this in concrete can really increase this stiffness. So let's take a look at just an example. So we have a representative tall building with a central core wall system, and we calculate the building stiffness by calculating its moment of inertia. Okay, now if we consider engaging the perimeter columns, and let's say we have 3x3 concrete columns, we now can just calculate the moment of inertia of those concrete columns as 240,000. And that's because the important component of calculating moment of inertia or stiffness is the distance away from the neutral axis that material rests. So this winds, if we add the column stiffness, we wind up increasing our overall building stiffness by almost 4 times. Now, if we look at the study using steel, we went in 14 by 873 is the largest available, is one of the largest available steel sections. So it winds up basically giving us about the same performance as the concrete column. But so then what happens if you combine the two together? So you combine the two together either by a circular CFT or a CFT column. So this is concrete in a tube, or you can place a steel section within a concrete element. So what this winds up doing, you're taking advantage of the concrete and the steel and further increasing your stiffness. So it's not only further increasing your stiffness, it increases your strength as well. So this is a very common solution when you have a steel floor framing system, because now you can use the steel within the perimeter columns to connect your floor framing. And the steel also helps reduce the issue of shortening in concrete, which we'll talk about a little bit later. And as Dennis started to get into accelerations, increasing your stiffness does help to control drift, and it does help to control accelerations, but likely sometimes you need to have more than just stiffness to control accelerations. Tall buildings, but especially the slender tall buildings we've been talking about, are susceptible to these increased accelerations. And one of the ways we can make buildings more comfortable from accelerations is to add mass, because mass will essentially slow down the building's motions. So one way that we can slow down the building's motions and add mass is to add dampers, the 2 mass dampers that like Dennis was talking about for Taipei 101. Here's the one that's at 432 Park Avenue. Now, this is a very slender building. But another approach to adding mass is to start with a concrete system, because concrete's weight automatically adds mass to the building. Now, this isn't just saying add more concrete. We still want to make an efficient concrete design, but just using concrete by itself adds more mass. So this is beneficial. It might not be enough, as this is also 432 Park Avenue, and you can see it's a concrete system. It still needs some supplemental damping, but at least it's an assistance. So building tall also requires a lot of resources, both materials and economic resources. So optimizing a building's height can really help to optimize the building's performance from a material and financial standpoint, because less height means less resources used for the same area. And then again, considering the same area, less height means less wind loading. And concrete can provide the thinnest floor system. So we look at a typical ceiling sandwich, and this happens to be one with a steel frame system. We see that the ceiling sandwich is dominated by the structure. And since this is a frame structure, it takes up a greater percentage. So if we can optimize the structural portion of this, we can then optimize a building's height. And considering concrete, a concrete flat plate system is the thinnest system you can build for tall buildings. So this is a continuous thickness flat slab. can efficiently span up to 30 feet. We can get more if we post tension it. Frame systems, you can span longer, but now you have the additional depth like we saw in the ceiling sandwich. So this isn't an option for all tall buildings, but it is an option to consider for multiple usages. It's not just for residential and hotel. We can do office with this as well. So in summary, concrete offers many advantages for tall building behavior because it inherently adds stiffness and mass. It provides opportunities for increased strength. It provides opportunities for minimum floor depth, and the concrete can be strategically used with steel to create composite systems. But there's other advantages. So concrete slabs have acoustic properties that make concrete floor systems a preferred choice for residential and hotel applications. It also has inherent fire resistance characteristics. And concrete construction can also be fast, especially if it's tuned to the needs of the formwork systems and the construction sequence requirements. So I just wanted to go through the lateral systems, which take advantage of concrete. So first is a core only. So this is where the lateral system's only the core. All the shear, all the overturning moment, all the stiffness is derived from that core. Now there's some limitations here because that core can only be so wide. So your footprint's only so wide. So then, because that's limiting just to have the core, the next step is to engage the perimeter. And we do this with first a direct outrigger. So this is where we have walls or trusses that rigidly tie the core to the perimeter. And it increases our building stiffness because now we've engaged the perimeter, and it also reduces our uplift. So the central core in an outrigger scheme really still resists most or all of the shear, while that perimeter structure assists in resisting the overturning. And these outriggers, they can connect to a mega column like we see here at Jin Mao, or they can connect to all the columns, or they can connect to a building frame. And an example of a system where all of the columns are individually tied with a direct outrigger is Burj Khalifa. Burj Khalifa is also a buttress core system, as we'll discuss in a minute, but it's also a direct outrigger system. And you can see here on the outrigger floor, we provided double story height walls to rigidly tie every column to the interior core wall system. So you can still get the same effects with an outrigger system by using what we call an indirect or virtual outrigger instead of a direct tie. So the way that these systems work is you have a belt wall that engages all of the perimeter columns and a thick concrete slab on the top and bottom of the belt wall. So you're creating a shear box. You don't have actually any internal rigid ties. So this is similar to an outrigger in that you're really resisting the motion of the building and you're engaging the perimeter. It's not as effective as a direct outrigger, but it can be very effective. In fact, one of the buildings I led the efforts on in Moscow, this was Europe's tallest building when it opened, 10-to-1 slenderness ratio, was Oko Tower, all residential. We have 4 belt wall zones on this building to create the indirect outrigger. So with core and outrigger systems, you can also connect to a frame, such as what's shown here in Tianjin CTF Finance Center. So this perimeter frame is designed to accommodate a certain percentage of the lateral loads through shear and also overturning. So it really is designed in conjunction with that concrete core. And here with CTF, we used concrete filled tube columns as well. Then we have a buttress core. So buttress core really was developed for Burj Khalifa. It's a system that uses geometry to provide stability. We have 3 wings protruding from a central core, and it's inherently stable because each wing is always buttressed by the other 2. It also uses load to create stability in that because of the significant tapers, as the building approaches the ground, it keeps getting wider and wider in its structural footprint. It keeps throwing load further and further away from the neutral axis, providing stability. And then the last system I want to highlight is what I'm calling a core plus a cantilever. So this is the same idea as a core only building, except now we've really expanded the footprint of the core to provide all of the necessary stiffness that we need for a building. The core carries all the gravity loads because we now cantilever all of the floor plates off of the core. So now we've got a really efficient system in terms of resisting lateral loads, in terms of the overturning moment, because now we have all the gravity loads to resist that uplift. A good example of this is the SOM design for Kingdom Tower that I worked on for quite a while. It is, and actually Kingdom Tower has that Thornton Tomaselli design is somewhat similar in that a lot of the floors are cantilevered off of the floor plates or off of the walls. So let's talk about the concrete that we use for tall buildings. We use conventional concrete, typically for the floor systems. We use high performance concrete, typically for the superstructure. And we use self-consolidating concrete for the foundations and any congested elements. Typical strengths for floor systems, we're in the 4 to 6 KSI range for concrete. High performance starts at 6, goes to 12 and beyond for the superstructure. Rebar, we use conventional 60 KSI, 80 KSI is very common. 100 is available in certain situations as well. So talking a little bit more about the concrete. So typical concrete is a mixture of aggregate, sand, cements, admixtures, and water. And one important metric to consider is the water to cement ratio. So it can be as high as 0.5 for conventional concrete and as low as 0.3 for high performance concrete, because one of the metrics of making concrete more of a high performance, high strength is reducing that water. So cement by itself, Portland cement, it is an important makeup of concrete, but it's also one where replacing a portion of the cement can be very beneficial. Because Portland cement by itself, it takes a lot of energy to produce Portland cement. So it's beneficial to replace some of it with something that isn't so carbon intensive. Plus, Portland cement generates a lot of heat as it cures. So for high performance concrete, it's typical to have up to 50% of replacement cements. When we use mass concrete, so really thick concrete where it can heat up even more, it's common to use up to 80%. So some common cement replacements, we have fly ash, ground granulated blast furnace slag, silica fume. These are all byproducts of the coal and steel industry, but they all provide advantageous properties to the mix. They slow down the hydration reaction, so they don't get the concrete to heat up as much. They increase the flowability of the mix, and they also increase the uniform density of the mix. So then there's admixtures that can be added to enhance the performance of concrete as well. So there's water reducing and specifically high range water reducing admixtures or superplasticizers that reduce the water in your concrete, reduces the water cement ratio, so it can increase the strength. You have retarders that slow down the heat of hydration. You have shrinkage reducing that limit the amount of shrinkage, shortening in concrete. Air entrainment helps with flowability. So does a viscosity modifier. So then what is high performance concrete? So that's what we really are using in super tall buildings. It's a high strength, high modulus, so very high stiffness concrete. And it's typical for tall buildings for walls and columns. Again, it's in the 6 to 12 KSI range, but higher strengths have been used. It uses enhanced aggregates and also lower water cement ratios by using superplasticizers, and it does use these cement replacements. So for high performance concrete for our tall building projects, it's common to not only specify a minimum strength like you do for all building projects, but a modulus that needs to be met as well. And additionally, there are other properties to a concrete design mix that need to be understood for a tall building. What are the creep and shrinkage characteristics? What is it a flowable mix because it needs to be pumped? How hot does it get? Because the concrete elements are all generally large. And then what is the durability or the finish? So I just wanted to walk through an example of a project that uses some high performance concrete. This is Merdeka 118. So this is going to be the second tallest building in the world sometime this year when it opens. It's just shy of 700 meters tall, mixed use, designed by Fender, Kitsaladis, Arup, and Samsung. So just an image showing where it stands next to its next to it, number 1 and number 3, once it becomes number 2. It's a concrete system. It uses a concrete core wall with 8 concrete mega systems, but it also is composite in that there's structural steel outrigger and belt trusses that engage these mega columns. It does have a high strength, high modulus concrete. So there's a rigorous testing program that Samsung went through with Arup to ensure that the right concrete was used, right, meaning the right performance that they were targeting. In fact, in order to make sure they had a consistency to all their concrete, Samsung actually reserved a large part of the quarry where all the aggregates were coming to make sure they're always getting the same aggregates. So the tests that you go through on a building like this to ensure you have the right concrete performance, you do your trial mix designs to arrive at what the mix design should be. Then you do your tests to confirm your strength, your modulus for that concrete. You do durability tests. It's important to do your creep and shrinkage tests so you understand what those properties are, so you can calculate how much the building's going to shorten. And you look at if it's pumpable, and then how hot the mix gets. And just some results from the highest strength concrete that Merdeka used, the C95 C100 105 concrete. You can see it reaches. This test is showing that it reaches its design strength, but that it also reaches its design modulus, and that the designers here did specify a stiffness that needed to be achieved in addition to the strength. So ensuring that the concrete's flowable and pumpable, there are tests that can be done to determine if the mix design and your system is appropriate. So this is the pumping test at Burj Khalifa that Samsung was also the contractor here. So they developed a test to determine the appropriateness of the mix for pumping up to 600 meters by laying all this horizontal piping with 180-degree bends to simulate the pressure. They also did a large-scale test cube to evaluate the heat of concrete. This was particularly for the foundation mix. And then there was a number of creep and shrinkage tests done where you develop cylinders of various different concrete mixes, and you put them through, this is a creep test was shown on the screen. And that way you can evaluate what the performance of that mix is from a creep standpoint. So another type of high performing concrete that's used for tall buildings is self-consolidating concrete. So this is a similar makeup as conventional concrete, but now we have added superplasticizer and added viscosity agents to increase the flowability of the mix. In fact, it's so fluid, it doesn't have a slump. You create a puddle with this concrete, like what's shown in the picture. It doesn't require vibration, but the key here is that it provides for assured compaction in highly congested areas like foundations or columns, outriggers, belt walls for tall buildings. So here's the Burj Khalifa foundation, and you can see all the reinforcement here. And here's the placement of the self-consolidating concrete mix. See, there's no vibrating crews. It's very fluid. It's reaching its own level, and it's getting in and around all of the congested reinforcement. But it's not only for foundations. It's often used in congested elements in the superstructure, like these belt walls. So in terms of constructing concrete, one key metric for constructing concrete is to minimize tower crane time, because the more you minimize the use of the crane, the quicker the more that crane can be used for other things besides constructing the concrete. So you'll use formwork systems that don't need the crane. You'll pump all the concrete to its point of delivery instead of using buckets, and then prefabricate rebar as much as you can on the ground, because that's really the only thing that the crane is used for in an optimized system for concrete. So in other words, you design the structure to facilitate construction. You understand the requirements of the limitation of the formwork systems, design and detail the reinforcement, considering congestion and the installation of those elements, and then design your system considering construction sequence. So when you're erecting a concrete tall building with a core, you can do it in two ways. You can do floor by floor, what's called stick built, or you can build it where the core advances beyond the floor by 10 to 15 stories. There's pros and cons to each. Most tall buildings are going to be done with the core ahead. It enables a faster construction schedule. However, it does create some more complex detailing at the floor to core wall connection. In looking at how these buildings then are erected, this is a concrete core with a concrete floor system where we have the concrete core being built ahead. So now we need to facilitate how you're constructed, how you're tying in the slab to the core. So you're going to use bend out bars like what's on the top, or you'll use couplers. Now, if you have a steel floor framing system and you're advancing the core ahead, then you'll have either embedded plates within the core, or you'll have post-fixed plates that you tie that steel construction into. You can also have jump form construction. So this is where you have individual panels of vertical formwork that you do need a crane to put into place. So this is typically done with stick-built applications. So this is just a picture of this type of formwork. Then you have slip form. So slip form is a vertical formwork where concrete's poured continuously into a continuously moving formwork. So when the concrete's being poured, the formwork is raised vertically at a speed that allows the concrete to harden before it is free from the formwork at the bottom. So this can be a fast erection method. It doesn't need the crane, but it's not very flexible in terms of geometry because it is continuously moving. So this is just an image of a slip form construction, a diagram showing how this process works. So a common system for tall buildings is automatic self-climbing formwork system, because this is really combining elements of jump forming and slip forming. So jump forming, you have the ability to modify on a floor by floor basis to some extent. Slip forming, you're using what you've just constructed to raise the formwork system without the use of a crane. Automatic self-climbing formwork system allows you to do both. So what this is pouring on a floor by floor basis, but the formwork system is supported by the floor it just placed. So a diagram here showing how this works. You have a few different levels to the formwork system. You'll have at the top where you're placing the rebar, you're getting ready to pour the concrete, and then you have the floor immediately below it that the formwork system is actually connected to, and then jacks itself up to the next floor. This is what was used on Burj Khalifa. It really helped to facilitate the construction, especially since most of the vertical elements on Burj were vertical walls. And this is just how the system is connected to the wall system. You've got these series of brackets that connect to the concrete that, again, has just been placed. And these brackets then, the rails go through these brackets and connect to the formwork system and connect to the platforms that are around the formwork system for the workers. And through these brackets and those rails, it can jack itself to the next level. Again, no crane time. That's the important key. Column formwork tend to be modular systems where you use the same form many times for many column sizes. So these are really they need to be moved around by the crane unless you tie your columns into the wall system like we did at Burj. That being said, there were some columns at Burj that weren't part of the wall system, and these were just individual forms that did go from floor to floor. Slab formwork systems, these are also modular systems. They're going to be supported locally by shoring posts. And you can either have many individual panels or you can combine them into tables depending on the system. So this is a typical formwork system that's a series of panels. This is how you can see them removing the panels. These systems don't require the crane time because typically they'll have a localized hoist that can move these panels from floor to floor. Or you could potentially use the crane and use what's called a table form. So this is combining many of those individual panels together. One thing we need to consider with concrete is floor systems is also how do we shore these floors. They'll need to be shored until the concrete reaches an appropriate strength so that you can release those forms. So typically when you're shoring these floors, you're going to go 2 to 3 stories below the floor you're pouring because you don't want to overstress the floor immediately below. So you're trying to spread out the load as much as you can. And this is an example of the shoring that's typically done under a concrete system. And I just wanted to walk through how all this works with a building like Burj Khalifa. So all of the vertical concrete, the wall concrete, was built with an automatic self-climbing formwork system. You've got the individual columns that are modular forms. What you can't see behind the protection for the workers are the slab forms, individual modular panels being used. And then you can see the shoring in place underneath those floors being constructed. But no matter what formwork system you select, the concrete still needs to be provided. So typically you're not going to bucket, you're going to use a pumping system because of the speed of it. So how this works is you have concrete trucks that come to the site and they deposit the concrete into a large series of pumps. And from these big pumps, it's delivered to a concrete boom at the point of deposit. Now, one challenge with concrete is that if you have a high performance concrete that's a lot higher strength than your floor, you can't compromise the integrity of the column or the vertical concrete. So you will potentially bucket a higher strength concrete in and puddle it around the columns. And it's important if you're going to use these concrete delivery systems that you're able to pump it in one stage to the point of delivery. So Burge had the world record at 605 meters for a single stage pump. That now has been surpassed by Merdeka. So finally, I just want to quickly go through some of the challenges with concrete, particularly how we coordinate our building services and how we accommodate creep and shrinkage, and how do we actually correct our buildings during construction for dimensions. So in terms of coordination, concrete core walls are typically very thick elements and they're dense. You're not going to be able to core drill your penetration. So you really need to be able to coordinate all of the distribution and the penetrations in advance. Oftentimes, a lot of this needs to go through the door openings, which are the link beams, of course. This is an image of what not to do. There's just too many penetrations in the link beam. So a better approach is to provide some penetrations, but to provide a zone underneath the structure to allow for all this all the services to traverse. But it's not only the link beams, we have to look at the walls too. And when we look at going through the walls, we have to look at, well, are there other chases that are behind the walls that we need to avoid? So in some respects, it starts to become a Swiss watch. Next is creep and shrinkage. So as concrete ages, it continues to change its dimension. And this can add up over a period of time to a significant number. The shortening can get up to, like at Burj Khalifa, we're about 4 millimeters per floor. And when you add that up, that's about 600 millimeters over the life of the building that Burj is going to shorten. And that's something we need to consider. How is that going to be accommodated? And when I say the shortening, it's because of creep and shrinkage. So creep is the amount, is the nature of concrete shortening or compressing as it experiences a sustained loading. So this is related to stress. So the more stress you have, the more creep you're going to have. Shrinkage is about the shortening and changing of dimension due to concrete as it's drying, as it's curing. So this is related to the volume to surface ratio. So the more surface you have, the more shrinkage you're going to get. And this is really an issue when you're comparing columns to walls, because you have completely different properties. Columns have higher stress than walls. Columns have different volume to surface ratios than walls. So you potentially have a difference between the two. So there are a few solutions. You can try to design the columns and walls for similar stress. That's tough to do because you just need a lot of area in your columns. One of the solutions is to make them more wall-like. Like what we've done on Burj Khalifa. That also helps to keep the volume to surface ratio similar. But you can also use belt walls or outriggers to basically re-equalize the loads every time you encounter an outrigger or belt wall. You can also use a correction program to adjust the concrete dimensions during construction. And that's why I want to close with it, just talking about a correction program, because anytime you have a tall concrete building of sufficient height, you'll need to have a correction program during construction that corrects for height and also the planned location. Because if you build a tall building to the theoretical wall floor to floor heights on a drawing, you will wind up with a shorter building at the end. So one approach is to design or to construct each floor to the theoretical elevation, which means you're going to be overpouring your floor heights, or you actually build the floors up even more than theoretical elevation, assuming that you're going to have shortening that then basically self-corrects itself. And in order to really understand this, you'll need to do a creep and shrinkage analysis of the structure to understand the magnitude of what type of correction you need to perform. And this creep and shrinkage analysis also considers the sequence of construction. And what we wind up getting is an understanding of what our wall shortening is going to be, what our column shortening is going to be, and then the really important metric, what the difference between the two are. And with that information, we can put together a correction program that then the contractor can use. And just to highlight one area of it, this is the wall correction. So this is that Oko Tower in Moscow. We came up with a correction program where we overbuilt the floors, the higher that we got in the tower, so that ultimately the tower would be at the theoretical elevation once the shortening was considered. So went through a lot of material. Thanks for your attention. Concrete, it's a great tall building material, but there's a lot that needs to be considered. A lot of advantages, but there's a lot that needs to be considered. So I guess with that.
Thank you very much.
All right. Well, thank you so much for having me today. It's really an honor to be here and to talk to you guys here. I think what you're going to see in my presentation is that you're going to hear a lot of the terms, and we're going to talk about a lot of the similar things that you've heard already. But in some sense, when we're talking about mass timber, you're also going to hear some things that are a little different, orders of magnitude. When we're talking tall, high-rise structures throughout, different materials throughout the world, we might be talking thousands of feet. Whereas with mass timber, we're really talking, hundreds of feet. And part of that is to do with the timeline and where we are and sort of the development of tall mass timber, similar to how, we've had 50 to 100 years of a lot of recent development in tall buildings. We're sort of just at the very infancy of that for mass timber. So I'm also going to maybe do a couple different things here, because I know mass timber means a lot of different things to a lot of different people. Some are very familiar with it, some are not. So I'm going to try to just sort of break my talk into a few things. What is mass timber at a real low or high level? Then talk about specifically where Ascent is located, kind of some of the building properties, and then really dig into some of the design considerations from a structural aspect, as well as really the key to tall mass timber at this day and age is permitting. How does it get permitted? And then I'll also talk about some of the construction aspects, as well as where I see the future of mass timber specific to high rise going. So real simply, I put a definition here of mass timber. And really one of the differences is when you think of, residential construction, or they call stick construction, is really the key is that word mass. And so it's the size of the timber you're using during construction, as well as really the game changer was the idea of these CLT panels, or really floor panels of any type, that were developed in Germany, I'll say maybe 20 years ago, which really sort of was the genesis for this new quote unquote mass timber versus what you've seen in the code as heavy timber for sort of glue laminated construction. Why would you want to use mass timber? There's a lot of reasons. Some of them listed here. We've touched on quite a bit. Sustainability. That's at the forefront of a lot of people's minds with this idea of a renewable resource and the lower emissions that are required for construction, but as well as aesthetics. When you're talking mass timber, you're likely going to want to expose it. That's one of the general benefits, and this idea of biophilia and the idea that people like this intrinsic beauty of the material itself. But there are also structural construction benefits. The idea of prefabrication and potentially increased speed of construction. Now, I know especially in Chicago, people would argue, if you're getting a 3-day floor cycle where you're doing a floor every 3 to 4 days, you may not be quicker than that, but there may be also other benefits in terms of how quickly you can fit things out. And as well as this idea of the weight of mass timber being far less dense than concrete, so you can potentially have lighter foundations. Again, I won't spend too much time on this, but this idea of this embodied carbon and the life of the tree, where it's absorbing the CO2 from our days in elementary to middle school science, and then sort of the extraction and the transportation and manufacturing of this product. A question I get a lot is that could it really be sustainable or environmentally friendly if you're cutting down trees to do this? A couple things I've learned throughout the process are, one, just as a frame of reference, it will only take 25 minutes to regrow the volume of wood that was used on Ascent, which is currently the world's tallest timber building. And also this idea of, other benefits there. I put a couple here, just what the CO2 benefits are in terms of equivalents, but it's also interesting to know that younger trees absorb more CO2. So this idea, if you're using a sustainable forest, when you actually cut down these trees, they actually plant new ones, which actually absorb more CO2. So there really is this cyclical benefit to the environment. I believe it was also mentioned by Anne at the start that this idea of high-rise mass timber or tall mass timber. These are just projects that have either been completed or near completion, but I promise you there's another, and I can talk to some on myself, another 10 to 20 projects that may be taller than Ascent in the very near future. So this is really just the start of where we are at the industry. So Ascent itself, it's on the sort of the lower east side of Milwaukee, if you're familiar with the area, just off of the lake, which is to the right to that photo. Something to keep in mind with mass timber, you've heard a lot about how important it is on tall buildings for coordination. That's sort of magnified, and I'll get into why that is for mass timber, but just keeping in mind there's lots of parts and players, but it's important that they're all sort of pulling in the same direction and that you're coordinated ahead of at a time, anytime you're using the idea of prefabrication. So Ascent itself, 19 stories of mass timber over a 6-story concrete podium with primarily parking, 284 feet tall, which is kind of funny when you heard we were talking about buildings that were thousands of feet tall, and the tallest mass timber building's 280 feet. But even that is roughly 4 to 5 times the size of the previous tallest mass timber building in the US at least. So just giving you some orders of magnitude there. It was approved under the Wisconsin Commercial Building Code, which uses 2015 IBC. That's the design code that it was utilized underneath. And to get it permitted, I'll get into this later, but in terms of a typical mass timber building in the US, normally you're limited to 75 feet. So we had to go through this alternate materials and provisions method in the code to get a variance for it. And when we were complete with the project, roughly 50% of the mass timber is exposed, and it's protected from fire through what's called the sacrificial char method, which I'll also get into in a little bit here. Typical floor plates. At the bottom, you have your PT parking levels. In the middle, you have your primarily residence levels for the main of the 18 of the 19 floors. And then at the roof, there's an amenity level. And I'll show you some pretty cool photos of these at the end. Structural system itself, at the base, as you would imagine for any high rise, typically there's deep foundations. For this one, we have concrete filled steel pipe piles. That's fairly common in Wisconsin. And one of the things we did on this, and it's probably fairly common for projects as well, is we static load tested the piles. And for orders of magnitude, when we're talking about using efficiency of materials, by load testing, we actually were able to nearly double the capacity of the piles versus what you would do in a standard code application. So same material strength, same size, just by testing it, we're able to verify nearly twice the capacity. And in doing this, we're also able to take advantage of the light weight of the structure above, right? Mass timber is significantly lighter than concrete. And one of the interesting things to see there, if you look in that bottom left photo, is that the 450 tons I noted were not a limitation of the pile itself or even the ground. It was just a limitation of the size of that frame they could use to test it. So by code, you need to essentially test to twice the capacity you're going to design to. And they pretty much had to stop at 450 tons because the frame couldn't take anymore. So base systems on the bottom right there is the typical podium level with 7.5 inch flat plate PT slab. And one of the things that was done is because it gave you a lower floor to floor height while it required more columns. It was slightly more efficient from a vertical allowance. But what it does is it gives this opportunity at the upper floors that if you're familiar with mass timber, the spans aren't quite the same as concrete. So what was required was this idea of a transfer level. So to sort of reconcile the grid that you would have for mass timber with the grid you would have for the PT parking level below. Now, one of the benefits we had was that at this level, there was also a pool that you can see in the upper left, as well as sort of a mechanical chase in the bottom and right. And for both of those, we had 6 to 7 feet of depth that were just required for architecture. And luckily, due to the light weight of the mass timber structure, we were able to minimize the PT beams to roughly 3.5 to 5 feet deep. But one of the interesting things that came about is because of the light weight of the mass timber, and that a majority of the mass timber weight was in the concrete topping slab poured on top of it at each floor, we actually had to stage stress the PT, meaning that they couldn't pull all of the tendons inside the PT at once, because if they did, the structure above was so light that you would have seen potentially cracks on the top of the slab. So they actually had to wait until they got about half of the mass of the building till they pulled all of the tendons. And so here's sort of the actual, the meat and potatoes of the structure. So this is the mass timber typical floor plate. CLT, if you know anything about it, cross-laminated timber panels are sort of the most common system for mass timber structures, but there are others, NLT, DLT. Typically, it can be a two-way system. That's one of the benefits. It's inherently stable because it's these boards that are glued in both directions, every other layer together. But in practice for structural engineers, usually it's designed as a one-way slab. And so what you see here is sort of up and down, you know, upper left to bottom right is the CLT panel that will span anywhere from 15 to 20 feet between those glulam beams that are spanning in the north to south direction at sort of a skip grid of anywhere from 20 to 25 feet. And then what you see there in the interior, those reinforced concrete cores. I'll get into why we use concrete cores as opposed to mass timber CLT shear walls a little bit later when we talk about the fire protection. But this just sort of gives you a general visual layout of what the mass timber structure looks like on a typical floor. In terms of the connections, there's sort of many different connections throughout the project, but really sort of two general beam to column connections that we utilized. When the structure was exposed in the end condition, we used what we call this framework connector. I'll get into why we use the word framework as well. That's actually a different project that was permitted in Portland, Oregon. And so what we did is you can see here, it's just sort of this beam or this haunch that actually gets fabricated in the shop. And then it comes to site, and then there's sort of this notch out in the beam with this plug at the base that protects it for fire. However, for the concealed conditions, what you see here is sort of a bread and butter, very simple bearing connection, but it's significantly more cost effective. So whenever possible, whenever we were concealing the wood, particularly at interior conditions where we weren't worried about sort of eccentric loads on either side, we tried to utilize this just from an economic standpoint. Right here is just sort of an isometric showing you the parts and pieces of the structure. So at the bottom, you have the podium, the concrete podium with the shear walls running up through the top. Then you have your glulam beams and columns. And then you have your CLT floor plates throughout the height. And I will see if this plays. Let's give it a shot. So you can just sort of see some of the parts and pieces coming together here. It's a quick isometric. Really, it is to some extent, if people, you know, compare it to Lincoln logs, and to some standpoint, it truly is with these sort of parts and pieces. I'll show you some photos later of how the team in the field actually erects the different parts and how they how very simply come together. So here we're up through the podium. You could sort of see half toned in there the transfers we talked about with the beams and columns being set. The team on the site said, I believe, if I remember correctly, that they had to be setting a beam or a column one every 7 minutes, or they would get behind schedule. So it just sort of gives you an idea of how quickly they put in these parts and pieces together. And by the end, I think they were doing one floor a week, roughly, maybe a little bit better. But, you know, by the time they figured out logistics, it was roughly one floor a week. Things to consider when you're talking about mass timber in general. So versus steel or concrete, one, we mentioned that you're probably going to want to expose the material. And each material, so species in this term, in terms of tree, have very different structural properties. So it's very important from an architectural standpoint that you're talking with the architect to understand what species would they like to use. Do they like a spruce that's more of a white, a Douglas fir that's more of a red, or a yellow southern pine? So they all have a different look, and depending on what one you want, they have significantly different structural properties that we need to take into consideration. Also, in terms of ascent, we actually ended up getting all of our wood from Austria. So one of the other challenges that brings in is that you're sort of using a different code in the United States. So all of the wood we got was sort of to Eurocode norms, so European standards. So one of the things we had to keep in mind is that we had to develop a process to verify the European grades in North America. So essentially what this meant is we had to do 3 designs. We did an NDS, which is the North American Design Specification design. We did a Eurocode design for the species in their own native code. And then we also did a hybrid design where we tried to take some engineering judgment to take the parameters from Europe and bring them into what they would be if it was in North America. Other things I had already mentioned, and I think people are aware that mass timber is significantly lighter than other materials. So this idea of acoustics and vibration, which aren't completely unique to mass timber, but sort of maybe magnified more than you would think about. And so for mass timber, you're typically going to have a CLT floor panel, which it shows there, On Ascent, ours were what they call 5-ply, so 5 cross laminations, roughly 7 inches thick. But then we had anywhere from 2 to 3 inch gypcrete, so lightweight concrete, a topping, as well as a sound mat on top of that for acoustical improvements. And then from a vibration standpoint, you can see there at the left, that's actually relatively new to the industry, but this idea that if you've designed anything in steel, you know, you've been doing this for years with sort of this vibration design guide and this sort of higher end analysis to verify that you're sort of within tolerable ranges for people's occupant comfort. This one should sound very familiar from Jim's previous presentation, this idea of vertical compensation and surveying. There's a picture there of Jeddah Tower. Now, obviously, we're not nearly as tall as any of those structures. However, what we found with there's really very little research into vertical compensation for tall mass timber just because it hasn't been around very long. But we really saw from our numbers that you're going to see anywhere from 2 to 3 times the vertical shrinking in mass timber versus a concrete structure. So, you know, you'd say a 25-story mass timber structure from a vertical compensation standpoint behaves more like a 75-story concrete structure. And so what we did for Ascent was we had a very sort of elaborate shim and surveying schedule. So essentially we asked the construction team on site every floor to survey the vertical elevation of all the structure. Excuse me, and we could compare that against what we had sort of calculated and or predicted. And then we could have them install in the field some steel shims in between the columns so that we could sort of in real time adjust the structure to what we anticipated the elevation would be. And then as Jim mentioned, we also sort of overcompensated, I'll say, for some of the columns with the understanding that over time it would actually come down and shrink a bit. One of the key things we've also talked about coordination among other trades with mass timber. There's a lot of stuff going into a small box. And because we got ours on Ascent from Europe, it had to be sort of coordinated ahead of time such that we couldn't go to the local Home Depot or the Lowe's to get a new timber panel if it wasn't correct. So everything had to be coordinated over, I think it was almost 100 coordination sessions with mechanical, electrical, plumbing engineers, the contractor, the structural engineer, the architect, to make sure that every screw was modeled in 3D ahead of time. So one, that there were no clashes with other screws. You can see there a beam and column connection where things get a little tight, but then also the idea of every one of these cores and penetrations through the slab, they actually came from overseas. So they had to be coordinated far ahead of time so that in the field, every penetration was in the right location. Because as I said, we can't get a new panel. If we had to wait for another panel to be shipped, you know, you would lose months and months of schedule on the project. And then sometimes, you know, you would be surprised that I've gotten, 15 minutes in the presentation and haven't talked about fire yet, which is, incredibly critical for mass timber construction. But I'll get into this, in a bit more when we start talking about the permit process, but this idea of fire performance for mass timber. All right, and so now the permitting process, a couple precedents that were important for Ascent. On the left there, you see T3. The reason that this is important is this was a Heinz project, I believe. It sort of proved that mass timber could be viable from a financial standpoint. We all want to do well for the environment. We want to do well for people and provide these products, but for them to make sense logistically and to do more of them, they need to be financially viable. So that was a big project for mass timber in the US. In the middle, there's Brock Commons, which for a long time was the tallest structure in North America. A very different system than Ascent, but actually all of the mass timber was concealed, but nonetheless a tall mass timber structure. And on the right, I won't embarrass myself by trying to give the name of that structure, but until Ascent, that was the tallest building in the world, and it's roughly, I think, 5 feet shorter than Ascent, so they're very comparable in terms of height. For anyone that knows anything about permitting of structures, for type 1 and 2 structures, which if you're dealing with high rises and tall buildings, you're probably in the type 1. There's some very clear language in the code that says you can't use non-combustible, or you can't use combustible materials rather. So the question becomes, well, how did we get the authorities to approve a tall mass timber structure? And here's sort of some of the visual things that we worked with through the city. When you're dealing with mass timber, you're likely in the type 3, 4, and 5 categories, which typically for an office and residential structure, you're limited to anywhere from 40 to 85 feet tall and roughly 5 to 6 stories. which is why the idea of ascent, which while it may not seem tall to some, it was significantly taller than what the code would under what I'll call prescriptive methods allow. So one of the ways around this is people for a long time have used this, what they call podium construction. So if you leave a 3-hour fire separation, you can utilize type 1A construction, which is likely your standard concrete construction, and then put the mass timber on top of that. Here's an example of a project that TT did that sort of took this approach to heart with a podium of concrete and then 5 stories of mass timber on top of that. One of the interesting things to look at when you're looking at sort of the growth of tall mass timber, the framework project that I mentioned, which was, unfortunately, it lost some funding, but was approved under a very similar process that I'm about to talk to you about here. It was 12 stories tall, which is almost twice as tall as sort of the previous tallest mass timber structure in the United States, all the way back in 2017. But then you can even see from there, so from, say 2015 to 2017, we doubled the height of a designed mass story structure. But then from 2017 to 2020, we once again over doubled that height with ascent. So you can see that very rapidly, almost exponentially, the height of mass timber is growing, because it's not limited necessarily by engineering, but more sort of finances and logistics having to do with the mass timber. So for ascent, what I mentioned is we use what's called this alternate materials provision. And the concept is this is in every code. And what the code essentially says is that the code is not there to limit any design in any way, shape, and form. All they want to do is make sure that they give a prescriptive method. And if you're going to use what's in the industry called a performance-based design, that your design meets sort of general quality, performance, and safety measures of any other design that would be using a prescriptive design. And so for mass timber, really the key there is, and sort of even highlighted and italicized, is this idea of fire resistance. So what we talked about with the city officials in Wisconsin is, ironically, Wisconsin actually removes the alternate materials provision from IBC in their code, but they replace it with some very similar language. So what we ended up doing as part of the permitting was that we permitted it as a type 4 structure, which is heavy timber, which is more or less what mass timber is. But we had a variance to say that we needed to provide the fire resistance ratings of a type 1A structure. So that's similar to any high-rise structure, with some provisions to reduce some of those ratings to type 2 or 1B, excuse me. And what that means in terms of actual numbers is that the columns in our structure were designed for 3 hours of fire rating, and the beams and slabs were designed for 2 hours, with some reductions allowed at the roof level. There's a couple different ways that you can get fire ratings on mass timber. You can use this idea of the char method, which if you think of sort of a bonfire, there's 2 different types of wood, right? When we talked about stick and mass timber, for a bonfire, you have sort of kindling, so very thin, small pieces of wood, and then large logs. And if you think of how that works, the large logs actually, if you can envision that, the outside of them chars, or you get this blackened layer. And what that does is that char actually protects the inside of the wood. So as it burns on the outside, the inside is still viable from a structural standpoint. So the outside actually protects it. And the idea of this char method is that over any given amount of time, based on research and sort of fundamentals of engineering, we can calculate how quickly that char will sort of encapsulate the column and how much it will dig into the column cross section, with the idea being that is if we oversize some of the columns and beams, we can actually make sure that in a fire event, so after 3 hours, the part that's inside of the charred section is still viable from a structural standpoint. So that's one way we can design for a fire rating. Another one would be to actually test the member, right? So we actually put it in a furnace. So for example, you see there at the bottom, this was done at the Forest Products Laboratory in Madison, Wisconsin. The current code does not have any testing for 3 hours, which is what I mentioned we needed for the columns. Reason being because no one ever needed it. No one has ever designed a tall mass timber structure to this size in North America before. So what we did was we actually had to test a column for 3 hours, which was really simply put, we put some sensors inside the column and we put it inside a furnace for 3 hours. And what you see there in that chart is we actually calculated how quickly that char rate grew inside the depth of the member to confirm that the equations in the code were at least conservative for that extra hour from hour 2 to 3. The other thing is you can actually test sort of the connection itself. What you see there is in the upper right, to figure out not just the members, but how the connection and the assembly performs as a unit. you can actually test the unit and you can actually load test it by doing that. And that's something I'm sure you guys are very familiar with at U of I. So there's a lot of different ways you could do it. On Ascent, we used all of them. So for the beams, we used the NDS design provisions for the char method. For the columns, as I mentioned, we actually had to do additional testing. So we actually tested up to 3 hours, as well as using sort of our own calculations and engineering judgment. And then for products, sort of like the CLT panels we got from the manufacturer, they actually do their own testing. So all their panels are tested in their laboratories and come with essentially a certificate saying that they've been tested for X hours of rating. So for our 5-ply panels, it was confirmed that they had been previously tested for a 2-hour fire rating. Now, from an engineering standpoint, we did our own calculations as well, but they do come with a certificate, which is nice when you're dealing with the authorities having jurisdiction. For the connection themselves, this was one of the trickier ones on Ascent. The reason we used what I called that framework connection is for the project, excuse me, in Portland, Oregon. Unfortunately, while it didn't go through and they didn't construct it, it was permitted and approved. And as part of that, they got a grant, a federal grant, and they actually did their own research on a fire connection, because up until this point, no connection had ever been rated for 2 hours. Because again, there wasn't a lot of tall mass timber, and normally those connections are only rated for 1 to maximum an hour and a half. But as part of their project, they needed a 2-hour rating as well. So they did this connection you see here, which looks very familiar to what you saw on the Ascent project. And so this one actually had been rated for 2 hours, which was the reason we used it on on Ascent. And it was part of the variance process, which with the city to verify and show to them that not just our members, but the connections themselves had been verified for 2-hour exposed condition rating. In addition to that, there's a whole lot that went into the variance process that has nothing to do with structure. One of them that does have something to do with structure is this idea of special inspections. Interestingly enough, in Wisconsin does not have special inspections. They don't use that part of the IBC code. However, for something of this sort of unique nature, everyone agreed that there should be special inspections for the mass timber frame. And as a result, I got licensed, or excuse me, certified as an IBC mass timber special inspector. But there were a whole host of other things you see here. This idea of utilizing the concrete cores, that was in discussions with the fire department. They just felt more comfortable with the concrete cores. This idea that during construction, that's the most likely time to have a fire on site. And the idea that if they had this, they could use these concrete cores to be self-standing. They were designed to span up the 25 floors by themselves without any concrete, without any steel, without any mass timber diaphragms, and that they could have an automated sprinkler system, dual water supply during construction, other things that you can see there, just to sort of make sure that everyone is going above and beyond that idea of the alternate material provisions, to make sure we were providing at least as safe a structure, if not more so, than if we were following the prescriptive methods there. So construction, some photos here, you can see sort of the development of this structure from early on when they're doing the concrete work to as they're actually structuring or constructing the mass timber floors, to the upper levels when they're nearing top out and they're actually putting on the facade. Sort of showing some of the different members we had throughout the project. We had glulam columns, beams, CLT panels, and then what we call these timber screws, which I'll get into in a minute here, because I know the contractors on site, these aren't necessarily the screws you're used to. These screws could be anywhere from, I'll say, 12 to 36 inches and upwards of nearly 1 inch in diameter. And so is just a point of reference, you see that guy there, that gentleman on site screwing in with that drill. The team had decided they didn't want to use cords for their drills. They wanted cordless drills. But due to the size and the torque required to get these screws in, they could only screw in, I think it was somewhere between 1 to 2 screws in one battery. So essentially what you don't see behind that gentleman is a giant bucket and a giant bin full of these batteries that they had to perpetually be charging, because essentially every 1 to 2 screws, they had to replace the battery in these drills. What you see here is 2 different types of columns being erected. The one on the left is what we had at the perimeter. So that column is going to be exposed, but also because it's on the edge of the building is what we would call unbalanced loading. So there's no loading on the outside of the building, but on the inside you have all the floor loading. So that was one type of column. And then on the right there is what we'd have as an interior column. It's got a little bit of a different connection, which we'll get into a bit, but this column is likely going to be concealed. So it's going to achieve its fire rating not by the wood itself, but it's going to be drywalled over so that the drywall will give it the fire protection that the system needs. You can start to see here when we were talking about sort of this idea of Lincoln logs, right? That with that framework connector, it really was just as simple as they could use the crane to bring in every one of these beams. But because that framework connector was already attached to the column when it was brought to site, they could literally just put the crane in, it just sort of falls into place. And then they put 2 screws on the bottom and it's done. So you set it and you forget it. And then here's the CLT panels, same thing. They sort of pick each one of these pieces has to be picked with the tower crane, which is why sort of logistics are so critical for mass timber, is that each of these members have to be picked up by the crane, which limits your time on site. And so it's so critical that not only do you have all these pieces that you know where they are, these actually got brought to the port of, I believe it was actually brought to Chicago. And then it was, I think via highway, via truck, they brought them to the port of Milwaukee. And then they brought them to site on a as needed basis. So on a day-to-day basis, those trucks you see there would show up. And then that would be right off the side of the building. And they would lift each of those panels with the crane, set them into place, and then move on to the next one. And each of those you can see right there, you can start to get an idea of how big some of these screws are and sort of what you're dealing with and how many hundreds or thousands of screws were utilized on this job and sort of the work of this team and that they put in to actually install all these panels. One of the nice things is with this system, once these panels are in place, your system is stable. Your diaphragm has been set. We didn't count on the gypcrete topping for the diaphragm. So once this CLT was locked in and screwed into place, they could actually take the shoring out underneath the structure and they could actually get to work installing the mechanical, electrical, fire protection, plumbing, all those good things they could actually get into below the structure right away. Versus if you're talking about a concrete structure, you may have levels of shoring that need to be left in place. And so it just gives you, while it might take a little longer to actually construct the floor itself, you get maybe earlier access to the floors below to sort of begin finishing out the space. And now talking about sort of the different mass timber connectors that you might see on the project. We had some column to column connections of 2 different types, whether or not they were exposed or concealed. Sort of the beam to column connections. We talked about a couple different ones of those. And then this idea of the connection from the core to the CLT and to the glulam beams. We have here, as you can see, the gentleman putting epoxy into the bottom of those holes. And then the column is sort of, again, used by the tower crane. It's sort of set over into place and then dropped into those little pockets. And that's where if we wanted to compensate this vertically, we would put a shim plate in there to sort of raise the elevation of that column anywhere from a 1/16 to 1/8 of an inch. This connection at the interior of the structure, this one is a sort of, the idea of financially, it's a simpler connection. It's just this fork sits in between the vertical part of the column below that sits up. And there's just screws that go into the sides. This column connection was used when we were actually going to conceal the column. So when we were going to have drywall, that gave this column and this connection its fire rating. And here, once again, this framework connector, where you can really see the simplicity where there's this slot that's installed into all the glulam beams. It's actually set into this knife plate or this bearing plate that's sitting off the column that came actually from Europe. And then once it's set, they install those screws right underneath, either 2 to 4 of them. And they're done. The beam's in place. As well as the simpler bearing connection, sort of less material, less parts, less pieces. But this is only utilized where we were able to conceal this at the interior of the structure. You can see here too some of the ideas of here's some of these braces that they utilize and how little bracing is actually required for a mass timber structure. This is during construction. So once they put on that CLT slab at the top and once it's installed, they can actually remove these braces, bring them up to the next level and start actually erecting all of the MEP elements on the floor below. Again, you can see sort of just these frames or these bents being installed in the field and the different parts and pieces. And sort of this view now below, you can see there's a little bit of water here. And one of the key things with mass timber, but no different than really any other project, is this mitigation of mass timber. This one was taken, and I promise you sort of minutes later, all this water is sort of squeegeed off, but it's critical between these elements, between these different prefabricated pieces. So the CLT panels is this idea of, you can see that tape and there's sort of a tar substance to make sure that you don't have water infiltration between the different levels. But you can see there in the upper left corner some of those prefabricated openings for mechanical routing or plumbing that came all the way from Europe and that were sort of installed, within, I believe they say, 1 millimeter or 2 tolerance. To make sure that everything's properly coordinated when it gets to site. The other thing is we've talked about vertical compensation. As you can imagine that the CLT and the mass timber move differently than the concrete cores. So what we had to do here is make sure that we not only compensated for the columns themselves, the mass timber columns, but also to understand how these things are going to move differently. What you can see there in the bottom right is this idea of we're trying to use these slotted connections inside these embeds in the concrete core, so that in the field that we could give the team some tolerance, some vertical tolerance that the contractor could set these connections at varying heights to make sure that the mass timber met up properly with the concrete elements, and that we gave them enough flexibility in the field to properly construct the structure. A few more here. This is the upper amenity level I mentioned. So these are 20 to 25 foot floor to floor heights. You can really start to get a feel for sort of the impressive, this biophilia, this idea of the beauty of the mass timber and sort of what it would look like with this space when all of this mass timber is going to be exposed. And you can see this is the one level of the structure where we had some sloping roof. So you can see the different panels being brought in for these very last connections. You can also see, if you see those holes at the top of the column, these were a unique column connection. If you can picture how lightweight mass timber is, we actually had to deal with uplift on these panels. And because it's so light, making sure that the panels didn't want to, I guess, quote unquote, fly away from the structure. So we actually had to hold down the structure with some additional, more robust connections. And due to the lightweight nature, we actually had to do this in some cases up to 3 floors until we got enough weight in the overall structure to make sure that it wouldn't want to, quote unquote, fly away. Again, just another picture of these being installed. And then a few real quickly interior renderings of sort of the finished space and what this sort of looked like once Ascent was completed. So with just a couple minutes, I think I have a few minutes left here, the idea of sort of the future of mass timber. With IBC 2021, there's obviously a bunch of new types, quote unquote, of construction with type 4, A, B, and C, allowing you to, versus in IBC 2015, only go 6 stories. Now you can go up to 18. The challenge though is even with 18, you have to be fully concealed. So even if Ascent had been built with IBC 2021, you would have still required a variance to expose the structure and go beyond 18 stories. One important thing to note is in the middle there, we have that type 4B construction. With the new IBC 2024, what's been approved, they'll allow you to expose 100% of the ceilings, which architecturally is a large benefit and something that I think you're going to see a lot of here in the near future. Something else to keep in mind, those limits that you just saw in the code are not structural, they're not a safety limit. It's simply that at the time of the codes, there wasn't enough fire testing to get I'll say, buy-in from all the code officials to update the code. And with that, the longer and the more often that we are interested in mass timber, the more research that's going to be done, the more testing that's done. And as a result, every time they complete another test, it's another data point that allows the city officials to sort of improve or enhance the allowable height or requirements of mass timber in the code. For Chicago specifically, again, this isn't the height of this isn't the height of Ascent, excuse me, but it's one that is, approved through the Standards and Test Committee, and it's proposed to be 9 stories tall, utilizing IBC 2021 and type 4B construction. In terms of the actual engineering, one of the most common things that people are looking at now is this idea of composite action. So similar if you have a metal deck on a steel building, utilizing that metal deck and the concrete, engaging with the steel beams, the idea of engaging the CLT with the concrete topping that you're likely going to have on top for acoustics. So whether it's nails or prefabricated systems, making sure that you can try to marry those two systems together. There's additional costs for all the connectors you see there and logistical challenges for the contractor, but also you can get the benefit of the two behaving structurally. You're also going to have a lot more testing, right? We had to use the framework test I mentioned because it was the only 2-hour test at the time. I know even since Ascent, there's at least 2 or 3 products that have been tested to 2 hours. The longer or the more often we use tall mass timber, the more products there's going to be more benefits, more options for the design team, which should reduce the cost of all those members. And last 2 I'll just talk about here is sort of this idea of a really more of a hybrid structure, right? So utilizing every material to the best of its ability. So if you want column-free spans, steel is likely going to be one of the beneficial ways to go about that. But this idea of sort of merging the steel beams with a CLT floor plate, minimizing the overall floor-to-floor depth, still getting the beauty of exposing the CLT floor, but getting some longer spans with the steel. Or this is another project we're working on right now at TT, the hybrid idea of concrete and CLT. And then in this sense, using the CLT really as formwork, stay in place formwork. and then having these concrete beams that then support these CLT panels, panels crossing span to span. So again, the idea that it's not, there has to be an economics involved with any project. It's not just a sustainability or structural, but it's making sure we're using all the materials and taking advantage of all their strengths and not trying to sort of shoehorn ourselves into using one material. Hopefully here, I think, apologies, maybe I ran a little long here, so there's not a lot of time for questions, but I'm happy to take any that there are if we have time for.
Thank you very much, Jordan. Really appreciate it. Wonderful. Excellent, excellent.
Thank you.
Excellent. We do have some questions in chat. Are you able to see? We're going to take maybe a couple of questions and
I don't see any, if you wouldn't
don't see-
mind, if you could.
okay. So let's see here. Let me just open my chat. How are the quality of mass timbers checked in the factory? Is one question.
Yeah, it's a good question. There's similar to how you would have in the field. I mean, you can imagine anytime you do prefabrication, there's going to be a higher level of quality simply because it's easier to control someone that's standing on the ground versus someone that's 80 feet up in the air hanging off the side of a building. But there also are standards and procedures in place. On Ascent, we made them provide us their own QA/QC manual prior to construction so that there was actually an inspector in the factory making sure that things were installed properly and in accordance with the code and any requirements we agreed to ahead of time.
Thank you. There's an interest in translating the CLT strengths from Eurocode. How did you do that?
Very carefully. So in some standpoints, sometimes they've already had engineering judgments where they actually have testing agencies that have come in and they essentially provide a judgment saying it's our opinion that based on these material strengths, this is how they are converted. Or that in some manufacturers have actually done testing. So it's in Europe, but they've actually tested to North American standards. I think that's something you're going to see a lot more in the near future. Generally speaking, Europe is a bit ahead of us and a bit's maybe generous to us, a bit ahead of North America in terms of mass timber. So some of the manufacturers over there, they simply have more, they can put more throughput through they're set up to do this. They have larger capacities. So I don't think Ascent's going to be the only system that has used European wood, but I also think on converse, as it becomes more popular in North America, you're going to see more CLT plants opening up. You're going to see a lot more of it in North America where we won't have to go to Europe for the quality or the quantity. You're going to be able to get it here for lower prices.
Great, thank you. Just for everyone's benefit, especially Matt, we're going to cut into the closing remarks, so we'll give you more time for people to ask questions. So let me ask, Jordan, there's a question, is it required to do any preventative maintenance for high-rise buildings? How are they quality mass timber checked in the, well, that we already answered.
Yep.
Yeah.
Yep. It's in if you look in the new IBC codes, they actually have they put some requirements on ownership to essentially make sure that they're not necessarily maintenance, but that they're checking I don't know if it's every year, every so many years, that they're actually checking on the structure to make sure that everything is sort of intact and that there haven't been any issues with the use and occupancy of the structure.
Okay. Next question is, do the slotted connections at the concrete core allow for future drying shrinkage, or are they locked into place after erection?
Yep. In theory, they could be, but they're locked into place. What we worked with the contractors, we tried to wait as long as physically possible to lock those in to allow for as much movement as possible. But as you can imagine, from a practical standpoint and an idea of a construction standpoint, there's only so much time we can allow, before those need to be locked in. Otherwise, we sort of delay the construction sequencing. But that's sort of why it's critical that we sort of anticipate maybe overcompensating so that at the start of construction, it's maybe a little high, but over time, it'll be level to maybe it'll be slightly below at the end. It's just working with the ownership team and the other trades to understand that this building is going to move. And we just everyone needs to be comfortable with that.
The next question essentially has to do with the type of structural system. The comment says basically looks like it's so far it's concrete core and hinged frames. Are there any considerations or anything going on in terms of possibly moment frames or outriggers?
Yep, so no moment frames, no outriggers were needed for this system. I thought where you're gonna go is because one of the questions in terms of seismic, right? So we did this in Wisconsin, which was, we were governed by wind because we're just off the lake, but Wisconsin has very low seismicity. But interestingly enough, the framework connector was actually tested in Portland, Oregon. So it was a little more complicated, and we've shown that it's actually been tested for additional ductility around the columns. So this one, no, the Ascent one was very, I'll say simple, just due to the sort of the requirements and the low seismicity. But there are other considerations, particularly if you're going sort of to West Coast where you have more seismic considerations.
Thank you. Last question, does mass timber have any restrictions on MEP design, shafts, routing systems, and so forth?
Yeah, in terms of routing, I guess I can't speak to that, but one of the big things that comes up is the idea of concealed spaces. So when you have combustible materials, you generally speaking don't want concealed spaces for sort of obvious reasons. So the idea of whenever you're going to have this concealed space, either having to drywall around those elements or just making sure fundamentally sort of it's a different structural check when you need these large holes versus sort of from a fire rating standpoint. At the time of Ascent, there were no products, for example, that allowed for a penetration through a beam that could seal it from both directions. Because typically Hilti's products are made to seal a floor slab, for example, where you're really only just trying to seal from one direction. But actually now that's not the case. So on Ascent, we actually had to design any penetration so that it would char all around the opening. So even a 2-inch opening, I had to treat as an 8-inch opening structurally. But now since Ascent, they actually have products that can seal it from both sides to sort of simplify this procedure in the framing of MEP around the structure.
Great. Well, thank you so very much again, Jordan. I really appreciate it.
Yeah, my pleasure.
Keeping the answers to the questions brief as well. So great.
My pleasure.
So let's move on to the last presentation and my most favorite material, steel, of course. So our next presenter, and Matt, if you forgive me, will not go to the slides to introduce you. That will take me a couple of minutes, so we'll give that couple of minutes to you. Matt is a principal at Magnuson Klemensic Associates, or MKA, and a member of the firm's office specialist group. His design experience ranges from low-rise, multi-building office campus headquarters to high-rise office mixed-use projects throughout the United States. He has applied his expertise to the design of many signature structures, such as Seattle's Amazon Block 20, Salesforce Towers in Chicago, Boston's Back Bay Station, and numerous heavy timber office buildings. In addition, Matt is actively involved in MKA's high-rise and office technical specialist team, the Structural Engineers Association of Illinois, and the Council of Tall Buildings and Urban Habitat. And again, as I mentioned earlier, Matt is another excellent example of our graduates, what you can do with our degree. Matt is a graduate of our program with the structures. At that time, it wasn't a concentration, but with that, we'll turn it over to you, Matt, and I'll make my closing remarks very, very brief. I'll just thank everybody. So because we're behind, we'll give you that time. So go ahead, Matt.
No worries.
Thank you.
And you can hear me okay, and you're seeing my screen?
Yes.
All right,
Yes,
great.
we see your screen.
All right, great. Thank you, Abbas. So I get the coveted 4:30 slot on a Friday where it's 80 degrees in mid-April. So I'm sure you're all excited to sit here and learn about steel. So I'll do my best to keep this interesting and hopefully keep you along for the whole ride here. All right, so the emphasis today is how we can take concepts, materials, and technologies and push them further, and how we can take innovations in some of these unique one-off structures like you're seeing on the screen and find ways to make them applicable for broader use in the industry, and finding ways that can make this more efficient for the broader use. Consistent with what you heard from Dennis and Jim earlier, it's important to recognize that any given singular material is not the right solution for the entire system. Just like Jordan had in the Ascent, like it's a concrete core. It's important to use the right material for the right application. So I want to highlight where steel has its benefits in the building industry. So quick highlight, I'm going to walk through these different concepts through a series of case studies on different buildings that I've been involved in to present steel solutions that build upon past knowledge and applying solutions to these project-specific problems that can then be extrapolated to the next project. And I really want to emphasize also the utilization of research and innovation to progress the industry. And, also noting that, U of I with the incredible civil engineering program and their research laboratory to, also work to be engaged with the University of Illinois, just as we are partnered with on many other research ventures. And also to encourage you, the students, or even working professionals, to look into the MKA Foundation. You can find our website where you can apply for grants, where we're funding research in the spirit of innovation and non-proprietary distribution of knowledge. So, as we noted, use material where it wants to be utilized, and there's applications where there's varying reasons that dictate what material is the right solution for us. So, even though we're in the tall building conference, I'm starting here with a bit of a shorter 19-story building, but I promise we'll get taller as we go. But conceptually, the idea here is, how are we utilizing steel to resolve constraints, whether it's schedule constraints for construction and trying to deliver the product, site constraints, or just local construction practice that often dictates what type of material is the right solution to any given project or any given structural challenge. So on any given project, we will draw up multiple schemes with differing materials to find out what's the right solution for this project based on cost and schedule. And that's true for the gravity systems and the lateral systems. So unique to this project, 145 Broadway in Cambridge, is that the schedule, given that we have 5 stories below grade in a really fast construction schedule, because they had a tenant signed on, a full building tenant, schedule was critical and of the essence, and that dictated an up-down construction sequence. So without going too deep into up-down construction here today, that essentially this picture on the left has all of the foundations are installed from grade, and we're going to plug the building into those little steel stubs sticking up and excavate down at the same time as you go up. So this really wants to be a steel column springing up, but at 250 feet tall, that's starting to push the limits on a braced frame system. But we needed to make that transition from steel as efficient as possible. And so while we might have wanted to tip the scales to a concrete core, we kind of pulled out the stops to find a hybrid system that could let us incorporate this up-down construction. So a quick elevation here of the below grade frame. So all of our lateral force is transferred out at level 1, and that's dictated by that sequencing that those steel braces are not able to be installed. By the time this building is topped out and enclosed, they're still excavating down underneath it. So we needed to be able to transfer all that load out at level 1. A quick illustration of the floor plan. You can see we've got a central core here. It's actually a fairly large floor plate, particularly with this trapezoidal shape, that we were challenged with managing the torsional period on the building. Was something that we really needed to rein in. And so we need to have a closed cell core, but even as the brace frame, we have a much less stiffness. What we'll find throughout the discussion here today is steel has a lot of great opportunities with the immense strength that it has, but at the end of the day, concrete has a lot of great stiffness properties given its area that allows us to implement this hybrid system to get the stiffness that we need. So despite wanting to have that closed cell core, it was critical to the architecture to have a big opening at the elevator lobby. So meaning that continuous box we had is kind of lost. And so to supplement that, again, that torsional box, that closed cell is what gives us a nice torsional stiffness. And so to supplement that loss, we introduced this idea of a steel plate shear wall, and we also utilize composite columns. The vertical stiffness of the columns and a brace frame stiffness is very impactful on the building periods and most also the torsional period of the building. So illustrating on plan, we've got these steel plate shear walls, and each of the core columns are the concrete encased steel columns. So this image is showing the erection of the steel plate shear wall. You see that So they're erected as two-story panels, right along with the traditional steel framing of having a two-story tier. This picture is a little deceiving because they shop installed the upper plate in each panel, and then the lower plate was left out in order to allow them to plumb the steel into place. And then once everything was plumbed up, they installed the lower plates in each of these systems. And so here you can kind of see that image looking down what will be the elevator lobbies one day to kind of give you that gap. Quick introduction of that, steel plate shear wall mechanics. We have these horizontal, vertical boundary elements. When you push it over, you have this tension field action, so allowing the plate to buckle in one direction. And so this is modeled as a series of tension-only struts in our ETABS model. And here's a good shout out to the U of I research. We know this because of experimental testing that was done right up north there at the Newmark lab. I think it's a cool picture when I started reading into this research, working on this project, to see that those are actual steel plates that you can see that look like sheets of linen, and you can really see that tension field action is very real. So again, it's the application of that research that allows us to implement new ideas and innovations into our structures. So here we applied the data from that research to run a buckling analysis in a finite element model, noting that this building is a wind-controlled building and really stiffness controlled. And these steel plate shear walls were not provided for strength as much as they were for stiffness. So really our objective in this buckling analysis was to prove out that this buckling load, or the load that would cause this buckling, would never actually occur under an ultimate wind event, such that we didn't want to have any kind of topping. Like, even though it's not failing, we didn't want to have that plate buckling in any given wind event. And so we were able to prove out that we never reached that buckling load in these steel plates. So as I mentioned, while steel has a great strength to it, we needed the area to get the stiffness that was required. So this is the one, dog on steel that I'll put in this presentation, that in order to have the comparable area to these steel columns, we would have needed, these concrete columns, we would have needed 14 by 730s with 3-inch thick side plates, which would have added over 600 tons of steel to the project. So working with the contractor to come up with a solution to encase these in concrete to give us the stiffness, saved well over $1 million for this solution. But again, allowed us to proceed with the steel erection as the critical path, given that those concrete encasements are being provided for stiffness. They could proceed to erect and could trail behind with those concrete encasement operations. So you're seeing here with the shop drawings versus how it was actually erected in the field. And then here's some quick shots of the concrete encasement. Yes, there's detailing effort required with how they're going to form out the concrete around these steel columns. But again, that was off the critical path. So the steel structure is still running up above this to top out the building. And a few details here for how the rebar was detailed around the steel. And an image at the taller story. Note that we added stiffener plates because that, given the size of those large plates, we did get into some buckling issues. So we had to stiffen those up. And just a few other projects in the area where we were able to utilize our experiences at 145 Broadway to implement the same system, but kind of refresh the detailing and work more closely with the fabricator again to evolve how that is going to be shop fabricated and erected by the contractor. And another project down the street that is also utilizing a similar concept with the continued evolution of our lessons learned. So here I want to discuss how we can find more ways to implement material advances. So we recognize that steel has a baseline, 50 KSI is what we've always used, but now we have the ability to use higher strength steel. So here we are starting to get taller with our Salesforce Tower, Chicago. Some of the architecture students might have heard me present on this a few weeks ago down in Champaign. 60-story building that's about to have its first tenants move in here at the start of May. So we're excited about that. But here, I want to utilize this project to elaborate where we can find greater efficiencies with structural steel when we're controlled by strength and what's the right application for that. Just high level overview on the project. It's a traditional central concrete core with steel gravity framing that supports the slab on metal deck. So with the high-rise building, the floor framing represents the large majority of the structural quantities in a high-rise building. So getting the floor plates right is really key to the efficiency of a building. So we focus on getting those floor plates as efficient as possible with our layouts. But we also need to be aware of where we can find opportunities to reduce material quantities. There's great benefits to reducing the steel volume of a high-rise structure from an embodied carbon perspective, from an erection perspective, from a cost perspective. So when we've got loads of a 60-story building, in addition to some pretty significant unbraced lengths here at the base of the building, where these columns are 80 feet tall, only braced midway through, we're requiring the largest available steel shapes. And so that starts to dictate the erection sequencing, or not erection sequencing, but the crane capacities and the crane location and the crane sizing, which has rolling implications on the cost of the project. So finding ways to reduce these critical picks is really critical to the construction of a high-rise building. So as I mentioned, 50 KSI has always been the baseline of A992 steel. And so the introduction of A913 steel is a real game changer. But the biggest game changer is that we now have a domestic supplier of A913 steel with Nucor. ArcelorMittal has been providing their high star A913 product for a while, but it was challenging to get that into a project given that there wasn't competition for that. And so having the domestic supplier of Nucor at the table has really opened up the door to engage A913 high strength steel. It utilizes a unique quenching and self-tempering process that actually physically changes the metallurgical properties of the steel to give us these higher strengths, higher yield strengths that has all the benefits that we mentioned. So what we've done, in the spirit of how can we utilize this information, we still do not want to have anything in our drawings that are specifying something that's only available by one supplier. So when only ArcelorMittal was producing A913 steel, we would specify 50 KSI column sizes and then 65 KSI columns. So Salesforce Tower is one of the earliest projects where Nucor was also rolling their A913 rolled shapes domestically, which allowed us to up our baseline. So we did not even schedule 50 KSI columns. So now our baseline is 65 KSI columns. And then we actually triple scheduled our columns. So noting that since ArcelorMittal has 70 KSI and 80 KSI available, we scheduled all three of those sizes, and you can start to see the potential size reductions. And that's just very direct tonnage savings. It's a very linear savings in steel tonnages that, again, directly reduces the amount of the crane picks and the embodied carbon. So recognizing that steel columns end up weighing about a third of the total steel tonnage, somewhere between a quarter and a third of the steel tonnage on a high-rise building like this. We've got about 7,500 tons on this project. So given that 20% savings in material strength on these columns, that's saving nearly 10% of steel tonnage on the overall project, which is a very meaningful number from a cost perspective. Just another view of these, 80-foot long columns that are coming down, touching the building or touching the ground ever so slightly. And really, at the end of the day, they were too small because steel is so efficient that the architects actually wanted to clad them and make them a little bit bigger to feel a little bit more proportional with the building. So while we take advantage of the smaller footprint up in the leasable space, that's a big benefit of steel columns that we saw in Jim's presentation. when you're using concrete, there's a lot of great benefits of concrete, but you can also get to have fairly large sections that start to take up a lot of rentable space. Another application of A913 steel is the application, like where we have high axial loads such as columns. We also have that in outriggers. So as we've mentioned in the earlier presentations, it's a great way to increase the aspect ratio on a high-rise building like this, where our core is very dictated by architectural constraints of the core size around the primary elevator shafts and our core to glass span. So we really want to widen that stance as best we can. So we implemented these two-story outrigger trusses shown here in yellow. We have belt trusses around the perimeter to help distribute those loads around the outside of the building. And then again, the top core of the truss with the same configuration. So this is where we're able to utilize grade 65 steel, again, in the sense that, so yes, this is for the stiffness of the building, but in an outrigger, the stiffness comes from the geometry of the truss, and all the steel members are purely axially loaded. So given this is a strength demand, or controlled by the strength demand, we are able to specify grade 65 steel, which again, at this height of the building, managing the weight of some of these extraordinarily large, heavy members is critical to the erector to be able to have pieces that do not control the design of the tower crane layout, to give the contractor the flexibility that they need. And respecting that all of the challenges that come along with this erection. These trusses are all fabricated in the shop and fully erected, laying flat on the shop floor to make sure that when you get up here 40 stories in the air, all these parts and pieces stick together. And the last piece on the benefits of that grade 65 steel, not only did it help the member size, but it also helped the connection design of these trusses. Namely, in that we, not only from an erector standpoint, they want to avoid field welding, but from a structural engineering standpoint, we like to have that mechanical connection at something so critical as these outrigger trusses. And having that higher grade steel allowed us to get this to work as a bolted connection and not have to resort to a fully welded connection, which would have been much more time consuming and again, not preferred structurally. Just elaborating a bit more on some examples of use of A913 steel. 150 North Riverside, which I hope many of you have heard about before, is another steel framed office building with, of course, the extraordinary feature of that site constraint that pinched the building down to fit within the railroad tracks. Truthfully, the railroad tracks are only on one side of this core that in principle, you could have only sloped one side of this building, but given the extraordinary unbalanced loads that you could imagine and the gravity-induced overturning from these sloping columns, we also introduced a slope on the other side of these columns such that we could balance those gravity loads. And it's really just the unbalance of live loads that we had to manage. But the resulting forces from these sloping columns, again, you've got tremendously large vertical loads from supporting a 50-story building, and then you're taking it at an angle that this actually required the largest available, they're not really column shapes, so we ended up using them as columns, W36 by 925s, also in grade 65 steel. So again, utilizing that high grade steel to solve the constraint of these serious magnitude forces. And then at the end of the end bays, where we're not at the core, we had to balance that load all with steel framing outside of the core. So you see this vertical truss to help resolve those unbalanced forces, and then also a horizontal truss. Just noting on this sheet, as you see, not only do we have that 36 by 925, but they're back-to-back 925 grade 65 columns, where we've got these loads coming down, collecting 4 columns all into 2 points. Again, just some extraordinary forces that would only be resolved within a reasonable footprint with steel. And it's the shot of the horizontal truss that is utilized to help drag that unbalanced force back to the concrete core. And on the right-hand side, you can see that piggybacked W36 by 925 mega column. And then one more project here in Chicago, Chicago Union Station, another central concrete core building with perimeter steel framing. Oh,
I didn't get that.
sorry, you didn't get that. All right, there we go. There's Union Station. Includes so the key feature of Union Station is this plaza, the interface at the ground plane where the columns come down, and the architect Getch Partners wanted to touch the ground plane as minimally as possible with this expressive feature, which inherently attributed a lot of force. So another caveat to this A913 steel is that this project used, in lieu of those back-to-back 925 columns, they actually did built-up box columns and used the tailor-made steel, which is an A913 plate material that is produced by ArcelorMittal that allows you to use that high-strength material in custom built-up shapes. And then the other feature of Union Station is it was the first project in North America that utilized the grade 80 KSI steel, again, rolled by Arcelor, that considerably reduce the steel tonnage on this project as well. Also implemented from a procurement perspective as a triple scheduled column, such that we could get competitive pricing from different fabricators that were utilizing Nucor or Arcelor steel. So switching gears here quickly to the evolution of innovations. I trust that many of you have hopefully seen many of the stories about Rainier Square. This was presented at the recent structural engineering conference by Dr. Varma of Purdue, who we've collaborated closely with. So I won't go into the details on SpeedCore, but what I really want to focus on here is how to evolve that innovation. Kind of the MK mantra is always strive for better. And so when we create this new system, what can we learn from it and how can we evolve it over time? Really high level, if you haven't heard of it, we're trying to replace the idea of a traditional concrete leading core that takes a lot longer on the schedule to allow the concrete core to get ahead of the steel framing, given how fast the steel erectors can build up their framing. And so conceptually, it's the same layout as a concrete core. This building happens to also be utilizing outriggers. That has nothing to do with the SpeedCore aspect of it, but just kind of illustrating that it's, this actually was originally designed as a concrete core building. It's, this series of cross ties that, the composite plate shear wall system is this panelized system, 2 steel plates sandwiched together, kind of like an ice cream sandwich that allows these plate panels to be erected with the steel frame. So this core is going up at the steel prefabricated panels that are shipped to site. Again, as kind of was discussed earlier in the symposium, the idea of modular construction. This isn't, so this is an evolution of how do we modularize the construction of lateral system in the core and allow that to go up faster. So there was a lot of technical scrutiny that went into the design and the peer review of this tower. A lot of that data that was utilized in our design was, again, produced by research at Purdue University that allowed us to implement that data into our analysis, work closely with peer reviewers in the city of Seattle to get this permitted. But given that ongoing at the time of this project, we were still working to get the research results of fireproofing. So one of the concessions in Seattle at Rainier Tower was that we would spray on cementitious fireproofing across the entire core, because again, we didn't have those research results. This is the first building ever to utilize this system, and it happens to be a 60-story building in a high seismic zone. So that was something that we accepted that we would utilize to help this project move forward. So the next evolution in the SpeedCore is how do we, given the cost and schedule implications of spray-on fireproofing, how do we eliminate that? So our project 200 Park in San Jose is the next project that has now implemented the SpeedCore system. Again, this is only a 21-story building, but it's the step in the evolution of how we are implementing the SpeedCore. Plenty of tremendous amount of lessons learned from an erection and fabrication standpoint, but from an analysis perspective, the evolution of the fire engineering was something that was implemented at 200 Park. Just a few images. So very similar concept to what we saw at Rainier Square with these panelized systems. But recognizing that, how can we eliminate that costly and time-consuming spray-on fireproofing? Again, more work with the Purdue University and Dr. Varma that allowed us to prove out the anticipated performance of the system when exposed to fire, and essentially apply a fire rating to the system without having to apply a passive system like spray-on fireproofing. And then that information is utilized to build finite element models and component-based models that are calibrated with those experimental test results that allow us to calculate the fire resistance of these panels. And referencing, fire packages that, help us determine what type of heat you're utilizing to reference in these time-dependent curves that would allow us to look at not only the axial capacity of these walls, but also of the splice connections and how these pieces are all put together. And then, it's just a reference as a detailed plot we reviewed that splice connection capacity relative to that fire case based on those formulas that were produced from the experimental data. So resulting in no fireproofing on the primary wall panels. So we're still at this point, not enough research data to prove out that the connection points where the steel ties into the core, that still needed to be fireproof. You can see the girders on the right-hand side of this only needed to have local fireproofing, whereas the beam side was easier for the contractor and agreed upon that we would spray that whole upper panel where those beams were connecting. And so that's, the next advancement is the proof of not needing to do that layer of fireproofing up against the core as one more step in economy. Next innovation in SpeedCore is recognizing that the first two uses of SpeedCore were in high seismic regions in Seattle and San Jose. So we've now implemented this system in the East Coast in Boston, where we do have some seismic demands, but they do not control over the wind demands. And so what that allowed us to do is look at what are the controlling demands on the splices where we're not depending on the plates for ductility in high seismic application since we're wind controlled. So one of the time-consuming efforts on SpeedCore is the welding of these splice plates. How do you stack these panels together and make that splice, which again, in a seismic application required them to be fully welded for ductility. Now, this did not drive the overall duration of the construction because this was not the critical path. They're still erecting above this, but the labor of the miles of welding that had to happen is something that we want to get to the next step of how we can make that a bolted connection. So again, we're just looking at these typical horizontal and vertical splices between each panel and the boundary elements and finding ways to make this a bolted connection to, again, eliminate all of that field welding. But given that there's limited access or really no access to the inside of the panel, we've been brainstorming different concepts, more research with Purdue and also SUNY Buffalo about connection types, how we can get to a bolted connection. These have now been tested, whether we do a welded nut on the inside that allows you to bolt in from the outside only, or if you can imagine, right, we're having to fit all these ties, all these cross ties with no concrete in place. And so we cannot just continue to tighten those plates. And so one proposal was to use a pipe sleeve, kind of a compression pipe that gives you something to tension those bolts against. And, we also need to think about how that interfaces with erection. We've got these keeper plates. So a lot of pieces at hand here that we've interacted a lot with the construction industry, with erectors, fabricators, and also utilizing the data that we've come across and finding ways, we don't want to be specifying something proprietary, but the concept of here's a series of options that a contractor could use. Atlas Tube has produced the Shuriken nut keeper, where this is effectively tack welded in place on the inside of the wall that holds that nut in place that allows you to thread that bolt in from the outside. And we continue to get favorable results. Atlas has been very proactive in finding ways to progress the capacities, and they've now tested up to 1-inch diameter A490 bolts, which helps us significantly reduce the quantity of bolts required at these splice connections, but still giving that idea that we can still have a non-proprietary solution with welded nuts, just giving the contractor some optionality. And we take our ETABS model, still using shell elements, not, we have some modification properties that we've applied based on the research data, but looking at any given pier, we can look at the forces, right? We've got our strain diagram from the overturning moment and axial loads in a pier that allow us to, assess based on that strain diagram, what are the forces in those bolts. Again, kind of looking at that plot, okay, we've got this capacity, and when we overlay all the data points of our wind, seismic, fire load cases, what is the bolt configuration that we need, where we can use lesser strength, smaller diameter bolts, fewer quantity bolts is all something that we want to progress. And then just the real quick last point is to discuss the idea again of a modular system. So we've worked with AASC in their modular office study to again speed up the erection of these high-rise buildings with prefabrication. So this effort with the fast floor system is supported by research at Northeastern University outside of Boston, which is actually run by Dr. Jerry Hajar, former U of I professor, is helping us research this system where we've got a prefabricated floor plate that's all steel with steel beams and plate system that can be erected in place. A quick floor plan for reference where you can see that panelization, 3 panels per 30-foot bay, where we've got these prefabricated panels are either attached to the central core that could be embeds in concrete, or it could also be the speed core, right? Like that wants to be in an all steel frame system with a speed core would be the optimal application for a fast floor system that allows this entire frame to be erected concurrently without the use of concrete, or attaching, like where we've got girders at the end bays, just different mechanisms, all kind of in the progress of being researched. So the idea of this plate is to eliminate the concrete topping slab. So that's specifically what's being researched at Northeastern University, is the vibration attributes of these systems without concrete. We would introduce a raised access floor to mitigate, to give you that floor finish that would be expected to allow you to put whatever traditional floor finish, but without the concrete topping slab. You can see here, like, how do we address ideas of what's happening at the spandrel condition of prefabricated panels where we're coping the beam. And so the next step in this research is understanding what are the splice connections, how are we creating our diaphragm. So kind of the strength and diaphragm tests are the next levels of research that we're working through on the fast floor system. But this really has the potential to eliminate a lot of time and expense and a lot of embodied carbon by eliminating the concrete topping slab in a high-rise structure. And with that, I will conclude. Sorry for rushing through that so fast.
Thank you very much, Matt.